All right, good morning.
Good morning.
Welcome to day 2 of the TSGC Design Challenge. I'm Tim Urban, Director of Texas Space Grant, and with me are Talia Jurgens and Nina Martinez, and we're here to welcome you back to day 2. So congratulations to all the teams for a great afternoon yesterday. We had an inspiring talk from Tyler Gilliland from Intuitive Machines. And then the teams got to talk to each other about all the amazing things that they put into their projects this semester. So congratulations on all the perseverance that you put in this fall. A couple notes for our presentations today. Every team has 8 minutes to present. I'll be sitting over there. At 7 minutes, I'll stand up. That'll be your clue that you have 1 more minute. And then you have up to 3 minutes for Q&A. And I'll have to cut you off after that because we have to keep on schedule. There are tape marks on the floor. If you are not within the tape marks, you won't be on camera. So please stay within the tape marks. If you have a demo that you'd like to put on the floor or on the table, go ahead and let us know ahead of time so that our camera can adjust accordingly. With that, I'd like to welcome up our first team. So Tarleton Relis LTV is up first.
Testing.
There's also a handheld.
Good morning, everybody. We are Relis LTV. I am Nick, the team leader. On my right here, we have Saeed, who's the team deputy, and then going down the line for the rest of the team, we have Baron, Irving, Alyssa, and Yash. Our advisor for this semester was Dr. Sharifi, and our NASA mentor was Challen Lansdowne. And now I will hand it over to Baron for the presentation overview.
Thank you, Nick. So we're going to continue the presentation, starting off with the background and foundational research, then continue with the LTV design and LTV setup, then the wheel designs and testing and results, and future considerations. Finally, have a brief conclusion and time for questions. For our background, we were tasked with designing a lunar terrain vehicle, an LTV, to transport astronauts and supplies on lunar missions while combating challenges such as rough terrain and weight and power constraints. For our foundational research on the LTV, it is estimated to weigh 1,000 kilograms. When adding in NASA's requirement of a payload of 800 kilograms, it totals to a weight of 1,800 kilograms. We also have taken into consideration that on the lunar surface, it will be 1/6 the gravity of Earth. Now I'll pass it off to Irving for the LTV design.
Thank you, Mr. Barron. So in order to test our wheel designs, we have created a 3D printed vehicle in order to retrieve performance data at a smaller scale. This platform allows us to, okay, so the general circuitry of our LTV setup, our main power supply consists of 4 lithium-ion batteries in series. We also have a PWM speed controller to regulate the RPMs of the brushed motors, and a set of buck converters in series as well to regulate power distribution, or even power distributions, to each one of the motors. Now passing on to Ms. Alyssa.
Thank you. For our wheel design, 4 wheel designs were taken into consideration this semester. This is our control wheel design. It's based off of traditional wheels that are used on NASA Mars rovers. Design 1 incorporates a honeycomb design while using a revised version of Bridgestone airless tire spokes. Design 2 is essentially the same with an increased frequency of the pattern. And Design 3 uses a slattered pattern and is inspired by Michelin airless tires. Our FEA analysis was performed in order to get a better understanding of how the wheels act under load. Now passing it off to Yash.
Thank you, Alyssa. With our models now defined, we can now start to perform testing. But before we can do that, we first need to construct a testing apparatus. Our testing apparatus consists of a plywood box with a clear side with Quickcrete cement mixture on the inside. The reason we chose the Quickcrete cement is because we have found that that has similar properties to the lunar regolith, so we need that for our environmental testing. In this case, what we do, we have 2 batteries of tests. In this case, the first battery of tests are time trials, where we time a certain length, and from start to finish, we measure how fast it goes. The next battery of tests are a mix of traction and sinkage tests. We measure at a certain power how much the max traction and the maximum force that it generates, as well as how far the wheels sink into the ground. Now that we've concluded testing, I'll hand it over to Nick for data analysis.
Thank you, Yash. Just to give you guys an idea of how we did our testing, general overview. So for each power percentage, we did it 3 times, and then the average is shown here on the graph. And then for our errors, it is the error from that average as well. So our first testing right here is our time testing. A couple things to note here is that Design 3 ended up being our top design in terms of speed, but also that Design 2 was neck and neck with Design 3, pretty much within margin of error as well. So in the future, we're going to dive deeper into those wheels in terms of speed testing. And then next up, we did our friction force testing. So a couple things to note about this is that our control wheel ended up being the highest in our force, especially in our higher power percentages. And another thing to note here is that Design 3 did underperform compared to all of our other designs as well. And also that Design 2 has probably the best average results out of all of our wheels. And then this is our sinkage data here. So like I said, the control wheel had the most force, but it also ended up sinking the most as well. Design 3 had the least force, which caused it to sink the least as well. And then Design 2, once again, having kind of the best overall performance out of all these wheels. Some of our testing errors that we encountered, the inconsistent density of our Quickcrete mix was affecting our data. Human error in our time testing during the time trials. And then definitely some slack in our setup for the string and our force testing and sinkage testing. The slack would affect the data on that. And then also just non-ideal setup. We probably in the future are going to look for a more rigid setup for those tests. And also the pebbles in the Quickcrete would cause our wheels to jump during the sinkage, and the force testing causing inconsistent data to be outputted to our force gauge there. And now I'll hand the mic to Saida for future considerations.
To better our improvement, we were getting pebbles and dust stuck in our motor, so we want to improve the cover for our motor to get better dust mitigate. We also want to get a bigger test bed to have better time testing data, because all the test data are very similar for time. We also want to include incline testing, so we can, according to the NASA requirement for any wheel design, we want to conduct any dynamic FEA to get a better understanding of the actual LTV and how it will function. We want to improve on our suspension and wheel hub for the LTV we have over here, but we also want to conduct some testing with weights on it for a better understanding of how it will perform. In conclusion, overall Design 2 was the best when it comes to sinkage, weight, and also traction. But Design 2 and 3 had very similar results, but Design 3 was a little heavier, so we want to continue with Design 2 and 3. Thank you so much, TSGC, NASA, and Tarleton State University for giving us this opportunity. And if you guys have any questions, please feel free to ask.
You mentioned that as you had more sinkage, you had more force. What was the trade-off you were looking for? What is the optimal trade-off between the amount that your wheel sinks into the ground and the amount of force generated?
Great question. So when we're looking into our wheel designs, definitely want to avoid how the control wheel sank into the ground. That was way too much. But we also wanted to have kind of a middle ground on the force as well. So kind of, there is a bit of a trade-off. So like you notice with Design 3, there not much force to the ground there, and it didn't sink as much. But with Design 2, it had adequate force to the ground and didn't sink as bad as all the other wheels as well.
Yes.
Have you considered adding tread onto your option 2 to add more traction for those wheels?
Yes, one of the things that we might think about doing is maybe not doing an outer tread, but maybe adding kind of indentions into the wheel and having it still be solid around the outside as well.
All right, thank you, team.
Thank you so much.
Good morning, everyone. My name is Chloe Nahosa, along with my team members Liam Byron, John Hearn, Scott Eatman, and Tony Deal. Our project was the TTC 106 Lunar and Surface Habitat Module Manufacturing. So a little bit about Team Boss. We're first semester seniors at Texas State University. Fun fact, we're the first graduating class of mechanical engineers. And we're also intending to pursue this project for another semester. We're very excited to be here and talk to you today. So what exactly does our module need to accomplish? Of course, we want to design a habitat that's going to be suitable for both lunar and Martian surfaces, and we want to make sure that it's going to be as modular and scalable as possible. Some of the key functions that we want to address is ensuring that we're providing a pressurized vessel for the crew to work in, as well as structural integrity, thermally stable environment, as well as adequate working conditions for the crew. We want to make sure that we're protecting them from environmental hazards such as extreme temperatures, radiation, things of that nature. And we also want to make sure the module is going to have standardized connections to facilitate power, data, and resource integration.
So I just want to quickly go over the design process that we've been following. So for the first semester, we've been going through several stages. Our planning stage, we really wanted to make sure we had a good grasp on the scope of the project, so that included our statement of work and identifying our constraints. Then we went through concept development, and we identified a lot of different concepts, which you'll see in a second. But we really wanted to understand our value add to NASA's program with doing this project, and we determined that that was going to be taking a mission-proven concepts just a step further into some innovative territory. And where we are now is in our system-level design, so we've been creating the product architecture, defining our subsystems, figuring out how our final assembly should go together, and then beginning to plan for a detailed design of each subsystem where we break down and go further into those designs. So next semester, we plan to go further into the detailed design. We're going to review feedback from today and from our senior design day, revisit any assumptions that we had to make, and then finalize our designs for those subsystems.
So of course, where did we start? We started off by generating some ideas, and some more ideas, and some more ideas. And then we kind of took the main ideas out of all of those sketches, and we kind of broke them down into 4 main geometric forms. So the horizontal cylinder, the half cylinder, the dome, and the polygonal cell were our 4 main geometric shapes that we wanted to move forward with.
Based on those designs that we came up with, we ran a Q matrix, so we scored our different concepts on different criteria. And the cylindrical capsule shape came out on top, so we decided to move forward with that idea. And then in order to align with our goal to take the NASA existing designs a step further, we decided to go for a hybrid of an inflatable and a rigid shell design. So as you'll see here in a minute, we will create an inflatable inner structure surrounded by a rigid MMOD shielding. And that allows for us to have some modularity in the MMOD shielding, have repairability for long-term missions. So we, based on how those panels would attach, which you'll see in a second, we ran another view chart, and our clip-on quick connect panels scored the highest on that. So that's what we decided to move forward with. And once we're getting into system level design, we broke down our subsystems as such. We have our structural, radiation, and thermal subsystems, which we spent the most time on this semester. And we'll talk about those mostly in this presentation. But we also have our power, safety, and integration subsystem as well. And just to go quickly over our power subsystem, NASA designed and defined fission reactors as their primary power source of choice for the Mars mission. So that's what we mostly want to plan for to integrate with. The kilopower reactors that are in development are looking very promising for that. So that was what we had selected for the power source for our module.
Yeah, so like John said, we wanted to do a hybrid between an inflatable and a rigid structure. So our module will be an 8.5 meter diameter circular base to meet our 15 meters squared minimum floor area, and it will ship deflated, as you can see on the top left, and then inflate to a height at the center of 3 meters. The rubber bladders don't have a lot of rigidity, so we used what they used on the Bigelow beam module, and we added a Nextel and Kevlar structure around that. And then we wanted to have our panels be replaceable for easy repairability, so we added a metal ring and a metal dome on top that our panels can clip into.
So here we have 2 pictures of each style panel that we plan to have on our exterior structure. On the right is the vertical panel, on the left is the domed piece. Both will have a Whipple MMOD design inside. And we have a quick illustration of how we envision the exterior model to come together.
So this is our rendition of how we would actually package and assemble the module inside the payload pairing. We decided to go with the SLS Block 2 configuration with the 10 meter long concept. The main worry here is we want to make sure that we're keeping the center of gravity towards the lower end of the payload pairing. So heavier things are going to go on the bottom. That would be like our hardware, robotics, equipment, gas canisters, and things of that nature. At this stage, the inflatable is going to be completely decompressed, so that's going to go on top towards the center of the payload fairing, and then surrounding that circumferentially will be the external panels as well as on the top.
On the left here, we have our mass breakdown. Currently, we are sitting at 9,152 kilograms of a total 10,000 kilogram allowable mass. Each of our individual side panels is roughly 30 kilograms. This was designed so that on Mars, each of these panels would weigh roughly 30 pounds. This is so that one astronaut is able to maneuver and assemble it by themselves. For our material selection, we went through and analyzed multiple different materials, but we found that 2090 aluminum lithium alloy Temper 83 was the best choice for our design. It has high strength, high stiffness, good fatigue resistance. It's also lighter than many other aluminum alloys. For the internal pressure bladder, we are using Vectran and Kevlar fabric. This is flight tested on the Bigelow beam for the inflatable. For our outer surface stack, on top of our aluminum alloy, we are applying an allodyne chemical film, as well as an epoxy polyamide primer and white polyurethane top coat. For the interior inflatable, this is how the Bigelow inflatable does theirs. We're doing it the same way. For our FMEA, we wanted to make sure that nothing major is going to fail, so we went through it, especially for the external and inflatable structure. Finally, we're really happy with everything we've done so far. The habitat we designed meets all the constraints. In the next semester, we plan on going forward with analysis of all our work, as well as assessing weight reduction and ISRU possibilities. Thank you. Any questions? Yes?
Is the aluminum panels that you plan on using sufficient to protect the astronaut from the radiation for a prolonged period of time without the Earth's magnetic field?
Yes, so we had a radiation constraint for protection of 10 grams per square centimeter. That comes out to about 3.7 centimeters thickness of aluminum by itself. And we think with all of the layering that we have currently, that radiation constraint will be met. So not just the aluminum per se, but all of the layering.
Do you have empirical data to prove that?
We will have that later.
Did you consider, or why did you not consider using materials that you could find on Mars as opposed to bringing panels from Earth?
So primarily the reason that we decided to go for prefabricated panels was because we wanted something that was going to be mission ready and deployable. So we wanted an earlier timeline for being able to deploy this module. So we're shooting for having technology that it's at a higher readiness level, closer to currently developed. So really we're taking existing technology and reconfiguring it into a new package rather than developing something entirely new. That's what we shot for.
We also have plans on looking into both SLS and sulfur-based concrete. Yes?
So do you guys have any plans on any dust mitigation technology for when someone enters that habitat?
So as of right now, we haven't really gotten into looking into dust mitigation techniques. The exterior rigid shell is going to be the main, I guess the first primary defense against orbital debris and things of that nature. So we definitely have designed it to optimize being able to apply dust mitigation techniques in the future.
Thank you, team.
Hello, everybody. Oh, sorry. We are Pioneer 39. Our name is inspired actually from the NASA Launchpad 39, which, if you're unfamiliar, it's launched a lot of the really historical missions, like the Apollo missions. And then the Pioneer program, that's the program at NASA that sent a lot of probes and stuff like that to scout out the moon and things like that. So that's what inspired our name. This is our team here. I'm Micah March, I'm the team lead.
I'm Andrew Boyce, I'm co-design lead. We're the ones who can make it today. So our problem was we need to make a size DVA tool belt assembly or accessory. They must allow one-handed, preferably blind tool installation. Tool must be retained with single fault tolerance. And yeah. So our requirements is we need to keep under 2 pounds. It needs to fit within a 5" by 5" by 5" volume. Must sink in water. Required rotational must be under 1.5 inch-pounds. Supports 15-pound tool weight and must meet a factor of safety greater than 2. More requirements is that we can't have any sharp edges unless required. Must be protected and under 3 inches from the hands. No pinch points, and if there are some, they have to be labeled. We need holes and gaps to be under 5 or greater than 5 inches and under 1.4 inches to avoid entrapment. User grip areas must also be labeled. And then we can only use MBL approved materials and no regular PLA, and any 3D printed parts for our final design must have more than 75%.
So here's an idea of what design we ended up going with. It essentially consists of 3 basic concepts. One is the outer shell, and this is what, you can actually put it on now. One is the outer shell, and this is what contains what we call the prongs. The prongs would be the yellow one, and they're spring biased towards the center. The stem is what goes through that the shell, and the prongs, they kind of compress towards the center, hold it in place. You can show the next slide. That kind of gives you an idea of how it works. This is one of our earlier iterations. But essentially it works like this. I can show you here as well. So it's just one push in, twist, and you pull out. It's very simple. We didn't want to over-engineer this thing. We just wanted to keep the actuations motion-based, because the problem is that astronauts, they don't have the best peripheral vision with their suits on, and their gloves are also extremely thick. So just keeping it as easy as possible was a goal for us. It's literally just a matter of connecting this green thing here to your tool. Once we get the brackets fully thought out, it's just a matter of grabbing hold of let's say you have like a hand drill here, just grip it, twist it, and pull it out. For astronauts, it'd be very easy to do, despite how thick their gloves are. You can go to the next slide. This is a little bit of our design evolution.
So the first part of our design, one of our first parts of it is going to be our stem here. We started off with a sort of stem with a sliding centering. We quickly realized that we did not like that with how much instability that created. So we shifted over to our version 2 here. The notable changes are we added a wall right here on the bottom slide that allows the prongs to coat over it. And we actually meant for it to keep the prongs in there so it couldn't go anywhere, but it turned out being one of our main features of our product, or of our design. For the third version, we really were focusing on keeping the prongs going only where we wanted it. We didn't want any kind of misalignments or anything else like that. Then we got our shell right here. We started off with a really big, we didn't want to have to mess with the constraints yet. We wanted to be able to work our way down, start big. Version 2, we optimized it a little more. We added 2 plates to the design to help retain the prongs, because one of the first prongs we had was the prong would shoot out whenever we pull out the stem. And then major changes to version 3 is that instead of 2 plates, we added a single slide-in sleeve to keep the prongs in.
So one of the key things that we really wanted to make sure we were honed in on is the reliability of this product. So we utilize the robotics department of HCC. They have these robotic arms, and essentially you can program them to do any sorts of movements. So they handed me this thing, showed me how to turn it on, and said, from here, I have no idea what else to do. So we just, we programmed it eventually to be able to just do the exact actuations that it requires in order to use this product here. And so we set out to hit a specific goal, but before that we ran into some issues. After about 350 cycles, our prongs were demolished. But this was really valuable data. I mean, honestly, I was excited when I saw this because it showed me that there was a problem I didn't realize existed before. And now we were able to find a solution for it. And it was really just a matter of making some adjustments to infill settings with our 3D printer, as well as slight changes to the prong geometry. But the bottom line is, if we hadn't had this machine really stress tested and use it over and over and over, we wouldn't have caught this. So if you want to go to the next slide. This is actually another type of stress test we did.
So the minimum safety factor rating for our movement is 15 pounds. Right here we have us doing a test with one of our earlier models where we actually put it up to 45 pounds, and we were able to pick it up without any problems. We were able to actually use the device before and after doing that. And going off of his robot arm testing, we actually set a personal goal. We wanted to see how our tool would hold up to an astronaut using it hypothetically 40 times a day, every day for a full year. It came out to about 14,600 cycles. We currently are only able to use the robot arm when the lab's open. And so this current stem you see up here has actually been through a little over 11,000 cycles.
11,490 to be exact.
And this is going to be a 3D printed nylon filament material. And we plan to make this out of aluminum next semester.
Yeah, so based on what you see here, we've already implemented changes into our design to even make it more further robust. So you can see there's chips here and there. Those edges there, we plan to fill it in our stress tests online at least, or the stress tests we've done with using our software shows that it'll handle things like that much better and should be less of an issue. This is some more of our stress tests. As you can see right there, those edges are filleted now, and there's no red or anything like that over there. So you can see it handles stress pretty well now that we've noticed that issue with our robotic arm. This is a little bit on our prongs. Again, these handle stress fairly well. I would say we've demonstrated with the robot arm that it's essentially not an issue, especially when it's going to be made out of stronger materials. Yeah, so we can.
Something cool about our design also is that currently as it stands, we're not sure what material shell will be made out of next semester, but if we continue using something that is 3D printable, the ISS does have a 3D printer, and we could possibly send files up there and they could use stuff to replace anything that might break, including springs that they could print and the prongs they could reprint. Pretty much any part of this could be reprinted until they can get a brand new assembly.
Yeah, so for our conclusion, we basically just want to leave off saying we created something that so far, as we've tested to date, meets every constraint that we've tested at least. Going forward, I think it shows a lot of promise, and it is simple in concept, but I think that's our selling point really, is that it's not over-engineered. We kept it simple and it's robust and it works. So there's more that we need to go into next semester for sure, but that's pretty much where we're at right now.
All right, questions?
Question?
So to get more cycles out of this, have you guys ever considered using a lubricant? Because we have a lot of, in this case, mating bases that rotate and move around each other. And friction is always got to be held with some sort of lubricant.
So we've actually used some of it. We haven't gone too far into the research yet. That's something we're definitely going to be focusing on next semester, since we already have pretty good design going so far. So a lot of the stuff we're doing next semester is going to be materials research, lubricant research, all that kind of stuff. See what kind of materials are going to be best to use to interact in space between our stem, prong, shell, and everything like that.
Bottom line there, we have found a few already just in our materials research that are options that work even in space, despite the vacuum and despite the challenges with temperature ranges and things like that. We found some options that will work and will last for the duration that we're going for, which is a year after one-time application. So it should be good. Anything else?
Could you explain your material choices a little more? I know you said that you plan on using aluminum.
Yeah, so we plan on using aluminum. I'm actually not the materials guy on the team. We do have materials. He's playing the role as a materials specialist. Fortunately, he didn't make it today. So I would love to talk to you more about that, I guess later if he arrives.
He will be here later, so if you come find us at table 3, we can answer those kind of questions.
Anything else?
Thank you, team.
Oh my goodness, what room in here? Okay, let's get back.
So howdy everyone, we are 12th Man Biofrontier, and today we'll be presenting our development of the Astro Ring. So before we begin, I want to take a moment to introduce ourselves. I'm team leader, I'm Austin Ingold. This is our deputy leader, Ricardo, and these are our team members, Karsten and Rashik. We'd also like to take a moment to introduce our NASA mentor and our faculty advisor, Philip Augustine and Zachary Viennock. So to begin, I want to introduce our problem statement. So we know that in long-duration missions, astronauts currently face a major challenge, muscle atrophy. Despite the current countermeasures aboard the ISS and the Artemis, astronauts still lose a considerable amount of muscle mass over time. One of the biggest issues is that traditional equipment is often heavy and monotonous, requiring significant cost in a 2-hour time regimen. As missions become longer and the spacecraft becomes smaller, we can't keep relying on this equipment.
So what are some ways that people currently counter muscle atrophy? On the ISS, where there's no gravity to load the muscles and bones, we have ARED, the T2 treadmill, and the SIGA cycle. These are proven and effective countermeasures, however, they are extremely heavy, and they are costly, and they're very large. So on Artemis, where space is an important factor, NASA has developed this flywheel machine, which is extremely small, lightweight, and they can use this for 2 hours a day. However, the main exercises they can do is a rowing motion and a swanning motion. And for 2 hours a day, it can become a little monotonous. So we want to develop a supplementary countermeasure. How can we keep exercise engaging and effective within the confined space of an Artemis mission?
So interviews with 6 different experts within the field were conducted. Generally, it was advised that an exercise device used during spaceflight missions targets spaceflight related effects on the body, including muscle atrophy. It was also recommended that the device be small, lightweight, and fun to use for the astronauts. Our main user needs fell under 4 main categories: safety, performance, ease of use, and cost.
So specifically for safety, we want the device to not harm the user, the spacecraft, and our other considerations will be described later in the FM meeting. The device must maintain the muscle groups, and it should also last for the duration of the mission with 1 cycle of rigorous use. And most importantly, the device should be fun and engaging. Lightweight and soft grips that can accommodate different hand sizes are essential, allowing for the device to be comfortable and intuitive. This includes very repairable components. Finally, the device must be relatively inexpensive and stored in a small footprint, and it should not siphon energy from the spacecraft itself.
Our initial ideation process went through a lot of solutions. We looked at a lot of solutions, including a resistive wall climbing machine, a compressive exercise neck brace, and even an electrosimulation suit.
In order to finalize our ideation, we decided on using a Q decision matrix to compare key specifications of our device against the gold standard, the ARAD. By rank scoring each concept, we identified our strongest option, which led us to our final design, the Astro Ring. So, what was the inspiration behind this device? Well, we wanted to transform a traditional Pilates ring into a gaming exercise tool. We wanted to target specific muscle groups that were often undertrained with the flywheel and ultimately reduce spaceflight costs.
So the Pilates ring was a considerable inspiration since resistive exercises do not require gravity. While supplementing the flywheel, the ring increases endurance in pec, tri, delt, and lat and rhomboids. There's increased electromyographic activity of hip abductors and adductors, as well as the glutes. Deep core and abdominal muscles and the obliques are used, as well as quality of life improvements by improving the pelvic floor muscles as well. To facilitate our proof of concepts, we divided our subcomponents into 4 main categories: the ring handle structure, general use, data management, and FX management.
First proof of concept, can we fit electronics inside of the handle? Our CAD model the handle consistent with Pilates rings and fit the accelerometer into it while adding a detachable lid for easy maintenance.
Of course, it can be pretty hazardous to use a spring-like device in zero gravity within a confined space. As a result, we sought out to ensure safety by integrating Velcro into the design. Velcro would be integrated into the handle and the glove to ensure that the ring does not accelerate out of the user's hand.
Another research interest was heat dissipation. Since our electrical components are located within the handle, they produce a lot of heat, and we want to route that heat out. A highly conductive material will be used in the handles and in the sheath to move the heat to the outside of the ring, and an emissive material will be used to dissipate the heat effectively from the components in the LEDs.
Our final proof of concept involved data acquisition, where I wanted to add both a heartbeat sensor and force sensors in order to track workout intensity and applied force tracking. So in order to do that, I wanted to add a PVG heartbeat sensor within the gloves, which is shown in our multi-sim diagram. And for the full sensors, I wanted to measure peak repetition velocity, which is going to show us both the muscle power and the fatigue per astronaut.
So shown above is our current Astro Ring prototype. The ring will ensure resistive exercises, while also integrating Bop-It style gamification for fun and variety. The game will include Velcro for safety, as well as real-time exercise components within the handle and the glove. Finally, a protective sheath will be used to ensure safety and heat dissipation capabilities.
So how is this gamification going to work? Well, we have a small Adafruit microcontroller directly into the handle. This will provide all the games. It's powered by a 12-volt lithium-ion battery for upwards of 5 hours per charge. It also has a speaker driver, and it drives the LEDs for gamification purposes. We executed DFMA on it, and here's the big thing. We're going to hit some highlights. There looks to be some low risk. We have lots of data transfer, which will use a wire cable instead of Bluetooth. And then if anything fails in terms of electrical, like the LEDs or anything, every component in here is hot swappable.
For medium risk situations, such as the ring slipping out of an astronaut's hold, Velcro will be used as protective anchor points to ensure safety.
For high-risk failure modes, like fracture, the sheath will be used to mitigate it. Ring fracture while in storage can be mitigated by a rationing mechanism, which will release the tension variably throughout the ring. It will also be stored with Velcro when in storage. Battery leakage and explosion can be mitigated by the protective casing, which will isolate fumes and mitigate any damage. And incorrect posture while using the device can be mitigated by a safety and training video before use.
For future considerations, right now we only have just the Bop-It in mind as kind of a standalone device, but with the USB port we can integrate it with the computer for it as a controller. Games like Flappy Bird, Tetris, Pac-Man, tanks, all kinds of stuff. Very exciting.
For future safety countermeasures, a sliding detent lock or a press-fit lock will be used so we can adequately disperse the force throughout the entire ring as to not create an artificial weak point when we open the ring to release the tension. And the rationing mechanism I mentioned before will also be used to do this, and it will add further utility to the device as well. So in conclusion, the Astro Ring is a fun, portable, lightweight, supplementary countermeasure that will keep astronauts engaged during long duration space missions. Thank you so much. These are references, and open to any questions.
You mentioned using a bobbin to sort of gamify your device. How would that look? Sort of.
Yeah, so we have a speaker, a small speaker that's inside the handle along with these LED rings. The ability for this to change color and also move the LEDs while you're moving it, and also the accelerometer inside here will be able to do the game. So it'll say like do this amount of reps, do this kind of rep, and the accelerometer inside you'll be able to sense what reps you're doing and how much. Now if you fail to do the reps, then it calculates your high score, it keeps it per astronaut, and that's how we're going to promote that competitiveness amongst the group.
Do you expect to have any troubles keeping the accelerometer calibrated in space?
We don't expect to, but it can be calibrated via code. That's something that we're going to use as variables.
Did you say it would be wired, not loose, or?
The data collection.
Yeah, so the data collection can be wired. It's going to be housed like within the components as well, but it can be housed or can be wired to the Artemis in order to try to transfer the data. Or if we want to use any of the screens on the Artemis, like to use it as a controller, it can be. But it can also be standalone and detachable.
All right, thank you, team. Okay, we'll have a quick 6-minute break. We'll reconvene at 8:55. If the next 3 teams would get ready, please make sure you're ready. Cosmic Commanders, Team Bob, and Team Ether. Okay, welcome back. Please have a seat. Our next team is University of Houston Clear Lakes Cosmic Commanders.
Good morning, and thank you for being here. We are the Cosmic Commanders. My name is Brian Sharp, and I'm joined here today by Daniel Zacheski, Isaac Beeman, Cameron Fassbender, and Gerald Begay. As a brief overview of our presentation, we'll first start off with a brief introduction, and then move into system conceptual design, followed by engineering analysis, and then move into deployment and assembly plan, and wrap it up with a quick conclusion and time for questions. So as I said, we are the Cosmic Commanders, and this is the lab, or the Lunar Activity Space. The lab is a long-term lunar habitat designed to withstand the rigors of the moon's landscape. With a max capacity of up to 4 astronauts and a life cycle of 15 years, the lab is intended to serve a growing market that seeks to establish a permanent human presence on the moon. Moving on to system conceptual design, some of the constraints that we were faced with this project was obviously the module mass being compatible with a delivery method, as well as the usable floor area between 50 and 80 square meters, thermal survivability between the maximum and minimum lunar surface temperatures, as well as radiation protection with an aerial density of minimum 10 grams per centimeter squared, an assembly time of less than 30 days, and one of the assumptions that we made was, like the other team, that there is a kilopower style nuclear reactor in place on the moon to provide the module with power. Now to wrap up the system conceptual design, I'll now introduce Cameron Fassbender.
So for our habitat design, it is an elliptic cylinder, which just means it's a cylinder with 2 half ellipsoids on the ends. The pressure hole has on the cylindrical face a isorid lattice pattern, which provides lightweight strength. Our habitat has 2 levels, a lower level for research activities and an upper level for living quarters, and there is a ladder so that the astronauts can traverse between the levels. Covering the entirety of the pressure hole is our Whipple shield, which protects against micrometeorites and also reflects most of the UV, near-infrared and visible light produced by the sun that impinges upon our habitat. Inside the wall cavity is a large rotating shield which tracks the sun and provides active protection against the high-energy cosmic rays produced by the sun for our astronauts. And then on the lower level, we have a double chamber airlock. The outer chamber is intended for the astronauts to clean themselves from any regolith that gets on their suits, and the inner chamber is meant for the astronauts to put on and take off their spacesuits so that they do not track excess regolith into the habitat. For our leg structure, we have 4 collapsible and extendable legs with crushable aluminum. And then on the end of each leg is a jack screw so that the habitat can be leveled after it lands. Our total habitat weight is 13.5 tons, and then our total payload is 45 3/4 tons, which is just under our launch vehicle's maximum payload, which is 46 metric tons. And I'll now be passing off to Isaac.
Hello, I'm talking about the engineering analysis and validation. So we'll first talk about our internal pressure stresses, so hoop stress and longitudinal stress. We can see our hoop stress is 91 megapascals and our longitudinal is 45.51. Note is our yield strength for the material we chose is 530 megapascals. It's very strong aluminum alloy. We'll talk about compressive stresses as well. So this accounts for a lunar sky crane that's going to be our delivery vehicle onto the moon on top of our habitat, which is compressing against our hull. And our net axial stress, which is considering internal and that compressive stress, is 11.17 megapascals. With that, we need to consider buckling on our hull, and the critical buckling stress, which is what you do not want to exceed because you risk buckling, is 14.54 for our chosen geometry. And as you can see, 11.17 is what our net axial stress is, so we're below that, we're not at risk of buckling. Additionally, we have bending stress at the floor. We went with an aluminum honeycomb sandwich design for our floor. It's very stiff, and we came out with 17.2 megapascals of bending stress, which is far less than our yield strength for the material we chose. That's what the maximum expected force of 1,000 kilograms and a 1 meter radius at the very center of our floor, worst case scenario. So to recap, we talked about our internal pressure and our external compressive forces as well as the floor bending. For our distortion energy failure analysis, the von Mises stress came out to be 85.98 megapascals, which is far less than our yield strength of 530 megapascals. We're not at risk of failure with our design. I'm going to hand it off to Daniel for radiation analysis.
All right, thank you, Isaac. So going over the radiation, we kind of have the benefit here on Earth of being protected from cosmic radiation from our atmosphere and the magnetic field from the Earth. So we have to bring it with us to the moon. So like Cameron mentioned, we are going to have basically like a curtain design made of high-density polyethylene, HDPE for short. Think of it as like your garage door, how it goes up and down, except it's going to go left and right, and it's basically always going to be facing the sun, so it shields from the sun. Using the density of the high-density polyethylene and it being just shy of 9.5 centimeters thick, with the material we're going to be using with the aluminum, we're sitting at 10.26 grams per centimeter squared areal density, so we do meet that radiation protection as well. Moving into the thermal analysis, we are going to be going with a self-Whipple design, basically meaning you have a hard aluminum exterior plate, Kevlar and MLI mixed into each other, and then your pressure hull vessel as on the inside. And basically looking at the thermal analysis, it's basically going to be hitting each of those layers. Each layer is going to be separated by gaps, so the primary mode of heat transfer is going to be radiation and not conduction. There will be standoffs that will have some conduction to it, but we considered it negligible, so we basically just approach it as 100% radiation. And then if you remember on the model, that silver part on the gold part is actually radiators to help dissipate any heat from the inside that could be coming. And then go into the actual math behind the radiation for thermals. We ran 3 scenarios, one if every single side is hit by direct sunlight, one if 50% is in the sun, 50% in the darkness, and then one if it's 100% just in the darkness. Those 2 worst case scenarios of the 100%, we are looking at just over 8 degrees gain interior per hour, and then a loss of 6.5 roughly per hour in darkness. So those radiators do help with the gain of degrees per hour when it's in the sun, and then that kilopower style nuclear reactor will help us power heaters inside to help mitigate that temperature loss in the darkness. Now I will pass it over to Gerald for deployment and assembly.
All right, thank you, Daniel. So, go back here. So lunar deployment, getting our lab to the moon, we want to use the SLS Block 2 cargo due to its cargo capacity. And then delivery system, as mentioned before, it's going to be the Sky Crane. If you're familiar with the the Martian, the rovers, how they were landing, same method. And then for the landing area, we want to go for the Shackleton craters, pretty much aligned with all Artemis missions. That's an area of interest. And then for deployment, manufacturing and assembly. So the method of making the isogrid, aluminum isogrid, we're going to use the CNC process to form, and also to form it, we're going to have a heat it around the structure. It's called stretch forming. And then to weld it all, we're going to use the friction stir welding process that we also use for the legs and also the standoffs off the hull. And then, of course, any type of welding, we're going to use heat treatment, type of post-weld heat treatment for the stress relieving. And I'll hand it off to Brian.
So thank you, Gerald. For future work on this design, we plan to conduct FEA and CFD analysis for greater accuracy in our calculations, as well as explore some mass-reducing concepts. But to conclude, our design is an innovative and minimalist design that allows for astronauts to immediately habitate the moon. We'd like to thank you on behalf of the Cosmic Commanders for listening to our presentation. We have a slide with a QR code you guys can scan to see any of our references, and we'd like to open it up for questions now. Yes, sir.
So, in y'all's weight analysis, did you guys also think about putting extra of those plastic, I believe, radiation shields that you guys plan to use? Because for most plastics, they will deteriorate with that kind of radiation.
Right, so the plastic radiation shield is actually inside the module. It will be sent up pressurized, so it will not degrade a whole lot. It won't be exposed to the elements, won't be exposed to regolith. It is on the interior. Additionally, it is very heavy. It is extremely massive radiation shield, so bringing an extra is not necessarily feasible, but yeah. Yes, sir.
Does your design take into account life support systems?
Yes, yes it does. Yes.
Your device is incredibly heavy, if I may say so.
Yes.
Have you guys considered lighter alternatives that would produce the same effect that could potentially switch out?
Yeah, absolutely. To meet the constraints that we were given from the challenge in terms of the aero density, in terms of the usable floor space, this is what we could come up with. We've considered other designs, such as using regolith to pile up around the lunar habitat, but that's really, you need a massive rover, you need a bulldozer on the moon, and those are not things that we can just assume are there. So we wanted a design that's, can immediately be transported as soon as it touches down, it's ready to rock, so that was the intent. And in terms of being light, we used the Constellium Airware aluminum alloy, lithium aluminum alloy, pretty hot stuff in the aerospace community right now, and that's how we try to make it as light as possible. Thank you.
All right, thank you. Okay, next up, Tarleton and Team Bob. Good. All right.
Okay, now we go. Okay, good morning everyone. Hope you're all doing well. So, quick introductions. My name is Ashland Benson. I'm a senior electrical engineer from Tarleton State University. I'll let my colleagues introduce themselves real quick.
I am Ruben Ohms. I'm also a senior electrical engineer.
My name is Nathaniel Miner. I am a junior electrical engineering major.
So the project, if it will stay up there, is that something I'm doing or? So our project was radiation tolerant, some kind of microelectronic motor controller. Yeah. Okay, we're doing radiation tolerant DC-DC buck boost converter specifically for low voltages and small satellite applications for heliophysics and deep space exploration missions. With that, I'll pass it off to Nathan to explain a little more about our background.
All right, so in our case specifically, we decided to go for rad hardening in CubeSat missions. In recent years, we've seen a lot of heliophysics and solar exploration missions, such as the Sunrise and Cinema missions from NASA, as well as some deep space missions such as BioSentinel and Lunar Flashlight. So some radiation types that we'll come across whenever our CubeSats are in space are gamma rays, solar energetic particles, cosmic rays, single event, upsets, as well as destructive and non-destructive latch-ups. Moving on, why choose gallium nitride over regular MOSFETs? GaN-FETs are inherently more radiation tolerant. They are missing the gate oxide layer that is seen in usual silicon MOSFETs. GaN-FETs are also much smaller, which allows for larger scale integration. Also, later on we'll talk about how that helps with errors. And some prime applications include DC-DC converters, which is our topic in specific, as well as the onboard computing systems. With with that, I'll pass it on to my other team members.
All right, so from the EPS and from the solar panels, you're typically going to be looking at 12 to 24 volts. And so typically we'd be stepping that down to somewhere between 1.5 to 5 volts. And so we decided to choose a 4-switch buck boost converter, which can not only step it down, but also step it up in the case that's needed. So to give a brief understanding of how the system works, based on the switching signals that the circuit gets, it's going to store current in that metal inductor, and then that current is going to help the capacitor on the output maintain a certain voltage. So we get pretty stable voltages on the output.
So now looking at some of our simulations in LT-Spice and our results. So we found that, like I mentioned, we did an integrated 4-switch buck boost converter, but we found that specifically for stepping down the voltage, so the buck, so our fall times were especially good when compared to silicon MOSFET-based converters. They were also 4-switch as well. So on your right, that is the buck mode, so that green line at the top, that's the 12-volt input, stepping down to 4.8 volts there. We can also step down to 5 or 3.3. And then we noted a quick delineation between the fall time and full settling time. So the rise in fall time is where you are within a certain degree of accuracy of your target voltage. And we were seeing fall time sub 5 milliseconds, between 0.3 to half millisecond, which the benchmark for these 4-switch buck boost converters is about a millisecond for silicon MOSFET-based devices. And then over here is in boost mode, so this is with a 5-volt input, stepping it up to 8.5. We also did 9.4 volts. And then what this is showing is controlling the voltage levels based on the duty cycle. So that entire architecture, there's 4 switches in there. The entire architecture basically behaves as one switch when you're turning it on and off in your duty cycle. And then based on that, you can control where you want the voltages to sit. So this is having it with a 13-volt input going from 9.4 volts on that top trace to the bottom is just below about 7.2. So, and then obviously we can set it to any of the traces in between there based on how we adjust our duty cycle. So some future work that we want to do. It is not our capstone project, so we've been working on that as the semester is wrapping it up, but this project has been funded to actually breadboard and then put it on a PCB for the development and testing in TVAC, so do our thermal and vacuum testing, and that'll be after we develop a control setup, so the control signal using GAN devices as well. And we also want to experiment with using a combination of GAN and SOG, silicon on glass devices, to reduce some of the cost of the system while still maintaining that rad-hardened, more robust power electronics. And then we would like to eventually ship off our final PCB for radiation testing, which is what this figure is demonstrating. So thank you, and any questions?
Do you have a range of radiation levels you'd expect this to be tolerant against?
We wanted to start with, when we were doing our literature review, and kind of the focus that we wanted to stay on was we saw there were GAN devices being used in a 4-switch architecture like this. Due to their very high efficiency, they were being used for high power and high voltage applications. And we didn't see anywhere where they were being used for these lower voltage range, that 3.3, 1.8, and 5 for like avionics control systems on a spacecraft. So that's what we wanted to nail down first. And then we want to go to, okay, how radiation tolerant can we make it? And then what if we put like a conformal coating on top of that, on top of our device design? So,
thank you.
Yes?
I'm curious what kinds of amperages you guys are getting out of this, because for our design here, we actually use a couple of buck converters. Do you know what kind of
on the output or like what the actual architecture is running on?
Just for your general theorized output.
I do not remember the numbers off the top of my head, I'm sorry.
It's all in our LT Spice. I can get that for you in like 2 minutes if you would like to know. I can get that answer for you.
Oh, absolutely. I'll for sure come by later then, yeah.
Okay, yeah, I can get those answers for you real quick. Thank you.
Absolutely.
Yes, sir.
What about the oxide layer makes it susceptible to radiation?
So, looking at, I'm not a materials or like a solid state physics person. My understanding is more at the level of a transistor. I know there's just different parts of the transistor that are more susceptible, essentially like naturally soft and hardened to radiation. So like the silicon backplate is perfectly fine, but when you have that the gate oxide layer in the silicon MOSFET, it's susceptible to being overcharged by particularly solar energetic particles. So it creates a buildup of current that if it's too much at one time, there'll be a destructive latch up, or you can have a non-destructive latch up where it's too much current for the device's levels, but it'll propagate through the system. It's not quite enough to actually physically hurt that device. So yeah, it's just one that's susceptible specifically to solar energetic particles.
What kind of topologies, I guess, for your DC-DC buck loops did y'all use? Were y'all only going on the H-bridge 4-switch configuration, or were there other topologies that y'all researched?
So we did look at several different architectures on it.
Yeah, we did look at several, but we thought that the H-bridge was the best one.
And our testing in LT Spice kind of reflected that as well, with the H-bridge and then the decoupler on that. Anything else?
Thank you.
All right.
Okay, and next up, UT Tyler's Team Ether.
Good morning, everybody. We are Team Aether from the University of Texas at Tyler. We're all mechanical engineers, and our project is the development and manufacturing of a lunar and Martian surface habitat module. And with that, we're just going to jump right in.
So a little bit of background about our project. NASA hopes to send men to Mars sometime within the 2030s. This is part of the Humans to Mars program. It's an initiative that encompasses several programs like the Artemis, NASA's Gateway, Shapia. Ours is part of an evolving framework, part of the Moon to Mars architecture. Hopefully, we contribute to the infrastructure of surface modules. As for manufacturing and transport, all aspects of our system have to be proven and tested. Basically, we want to stress safety first. Basically, we want to stress safety first, and with the mindset of we're sending a family member to Mars. You know, you want to make sure they're taken care of, and safety is the first priority. Okay, so our concept statement is to design an extraterrestrial module suitable for both the lunar and Martian surface. It has to be fully prefabricated here on Earth, and has to be launched pressurized and configured, ready for immediate deployment.
So along with the objectives in that concept statement, our design is also informed by a series of specifications and constraints. Some of our specifications, we needed to ensure that our launch mass remained below 10,000 kilograms. We need to ensure that we achieve an internal surface area, floor space within our module greater than 50 square meters. We obviously needed to account for the intense thermal cycling on both the Moon and Mars. We need to make sure that our module will be able to withstand those intense conditions. We needed to account for the radiation, the solar radiation experience in both environments as well. And some of our constraints, the primary constraint that we were focusing on was ensuring that our module could fit within the fairing of a Falcon Heavy rocket, fully configured, fully prefabricated, and launching pressurized such that it would be ready for immediate deployment upon arriving on site on either the Moon or Mars. The combination of these objectives and these constraints led us to our design here, the Aether module. You can see by its shape, it's inspired by existing pressurized vessels such as propane tanks and high altitude aircrafts. Again, it's designed to stow and ship fully configured for the fairing of a Falcon Heavy rocket. This eliminates the need for assembly on site, streamlining the deployment process and mitigating risks faced by the crew members and mission success. We can see an internal look at our module here. We can see our floor space there. We have a primary workspace down below. This is where any hygiene stations or work interfaces would be for our crew. And then the two upper levels are lofts. These will be used for bunking for our crew members. Our module can support 4 crew members total. We have a pressure shell and end caps to withstand our 101 kPa or 1 atmosphere internal pressure within the module. The loads of our module, both the hoop stress caused by internal pressurization and the structural loading itself is supported by those rings you can see there, the internal support spine, and that's channeled into our external leg saddles, which support the module externally and anchor it to the lunar or Martian regolith.
I'll just be going over some of the material selections, so just give you the highlights. For our pressure shell, we're going to be using aluminum 2219. For the spine, it'll be aluminum 7050. For the legs and joints, it'll be titanium 1023, and the floor will be a plastic polypropylene. And we're going to be integrating an MMOD layer 2, specifically aluminum 6061 for the bumper panel and Kevlar for the fabric layer. For thermal, we're going to be using a utility gap as well as some MLI blankets that are aluminized Captain. And then we have a acoustic installation of Basotec foam and interior wall panel of Nomex honeycomb. And lastly, for radiation protection, we're going to be using a boron-infused HDPE.
So we conducted some FEA analysis on our module to validate our safety factors as well as locate any potential weak points. Example of this, a weak point we found when we conducted this analysis are the bolts which pinned our legs for the module. This inspired us to move from M10 titanium bolts to M16 bolts. After making that change, we achieved safety factors across our module globally of greater than 10, so structurally more than sufficient to withstand the loadings at play. Additional FEA analysis revealed that we have a maximum deflection of just over 1 millimeter across our module, and further validating the structural integrity of our design. So we can sum the mass of our components here, and we come out to a total structural mass of about 5,200 kilograms. And this is well below our spec of 10,000. It gives us a buffer where we can take a very generous estimate of the systems that we would need to populate our module with of 3,000 kilograms. It's a high-end estimation. We would still be well below that 10,000 kilogram specification, as well as even further below the launch mass payload limit of a Falcon Heavy rocket of 16,000 kilograms. And when we look at the total surface area we achieve with our main floor and our 2 lofts, we come out to 50.4 square meters of usable interior surface area for our crew members.
Okay, so here are our thermal control results. Our 10 millimeter multi-layer insulation blanket performs well over worst case temperature scenarios. As you can see in the cold case, we kept the heat loss to about 1340 watts, and that was for the moon. For the hot case, we kept it to heat gain of 490 watts. In the moon's south pole, so and 1700 watts in the equator of Mars. In the hot case, we limit heat gain to under 500 watts on the moon and heat loss to 62 watts on Mars. With thermal control address, we now turn to radiation shielding, protecting the crew from ionizing exposure. In the loft area, we implemented the HDPE, which was a high density polyethylene. Came out to a total radiation protection of 24 grams per centimeter squared. In the non-loft area, we solely relied on internal systems and structural layers on passive insulation and protection, coming out to a total of 10 grams per centimeter squared. We also did acoustic insulation equations. Now, so here's our conclusion. With every design choice from material selection, manufacturing method, structural analysis to thermal control and shielding was made with survivability and comfort in mind. We'd like to thank UT Tyler, TSGC, and NASA for this opportunity. We'd also like to thank our advisor, Dr. Mohammed Biswas, and our mentor, Mr. Knuckles. Thank you.
So I was wondering, based off of yesterday's discussion when he talked about the Louisiana Bridge and roads, have you guys considered having to transport this module over roads like that?
That's a great question. We actually had not considered that. I think it's something we definitely need to consider, but because our module is fairly small comparatively speaking, it's something that I think we would be able to work around.
So, like I asked for one of the habitat modules before, do you guys have any plans to add any dust mitigation technology, like some sort of like air lock to like clean off dust for astronauts before they enter the space?
So our module is designed to be part of a larger infrastructural base, so it would have, the port exiting our module would not be an individual airlock. It could exit into an external pressurized channel, which could link to an airlock or other modules. So dust mitigation is something that would be downstream of us.
How are those end caps attached to the main cylinder?
They're manufactured out of the same aluminum alloy 2219 as the pressure shell itself, so they can be affixed via friction stir welding.
How do you deliver the habitats to the landing location?
So they'll be landed in the Falcon Heavy, but we will be relying on, we're assuming that we would be able to rely on infrastructure present on Mars for the moon already, such as a boom crane. Our legs are designed to be hoisted by a boom crane and righted, and then dropped off to the surface, ready for commencing operations.
But how do you bring it from space down onto Mars?
The Falcon Heavy does have some issues with landing on Mars as of now, but our design is assuming that that will be a possibility in the future.
Thank you. Okay, we will take another quick break and resume at 9:40. Okay, good morning. Welcome back. We're going to get started with the second half of our morning presentations. First up for this session, University of Houston Clear Lake. Team Space Depot.
Thank you. Good morning, everyone. Welcome to Team Space Depot's presentation of the Passive Capture Tool Dock. My name is Arib Ahmad. This is Kareem Khalil, Viet Nguyen, and Ethan Fitzpatrick. Today we'll talk about the background, project goal, criteria and constraints, decision matrix, CAD analysis, conclusion, and then we'll open up for Q&A. Extravehicular activities, or EVAs, are critical to ISS maintenance. Currently, astronauts dock tools to their swing arms using manual locks or toggles. These can be very difficult to operate during long missions or with bulky EVA gloves. The idea is to improve on this and provide a way for astronauts to dock tools quickly, single-handedly, and without fine finger control. I now pass it on to Kareem to take us to the project goal.
Thank you, Arib. All right, so our main objective of this project is to design a passive retention docking system that is going to properly integrate with the mini workstation swing arms aboard the ISS. So this is going to enable astronauts to secure and retrieve the tools only using one hand while wearing these EVA gloves. This is going to improve the efficiency during these missions, and it's also going to reduce the fatigue of these astronauts. So we have 4 key design intents. We want passive operation. We want no external power or complex actuation for any of our mechanisms. We want it to be optimized for the limited dexterity of the gloves that these astronauts use. We want it to be very reliable. We want the tools to remain secure under vibration, sudden impacts, or any movements. And we want it to be fully integrated with the mini workstation bolt hole pattern, which is a 1 by 1 inch square bolt pattern. This is going to prevent tool loss and enhance EVA efficiency, and overall just reduce the astronauts' workload. This is the pistol grip tool. This is actually what we're designing the passive capture tool dock around. It's basically just the drill that they use on these EVA missions. I'm gonna go over some criteria and constraints. So we have some performance criteria. We want all of the mechanisms to be as simple and reliable. So just push, pull, or sliding motions. We want the whole device to be single-handedly used. Smooth integration with the swing arms, and we want it to be very reliable and durable and ergonomically designed for the gloves and the spacesuit. Some environmental and safety constraints is that it needs to operate in a vacuum, microgravity, and temperature extremes. We want no sharp edges, loose parts, or pinch points, and it must sink in the MBO training facility. Some physical constraints that we have is that we want the volume needs to be less than or equal to 5 by 5 by 5 inches, and the mass of the device needs to be less than or equal to 2 pounds. It needs to be able to carry a load of at least 15 pounds. And for any linear actuations, it needs to be less than or equal to 10 pounds force. And for any rotational actuations, it needs to be less than or equal to 1.5 inch pounds. And the same hole pattern needs to be 1 by 1 inch square. Some manufacturing constraints is that the material must appear on the MBL approved material list. If we decide to 3D print any components, it needs to be at least 75% infill, and any openings need to be less than 0.5 inches or greater than 1.4. This is going to prevent finger entrapments, and the factor of safety has to be greater than 2. This is our decision matrix, so we just have 6 different locking mechanisms, and we scored these, and this resulted in that the linear snap action and the T-handle pin lock were the top 2 locking mechanisms, and we incorporated that into a singular design, and I'm going to pass it on to Viet to talk about those designs.
Thank you, Kareem. So our conceptual design, this is going to be our conceptual design that combines both of our top 2 locking mechanisms from our decision matrix. It's going to be our snap action and our body tent lock. So the entire device is going to be around 2.5 by 2.4 inches, so it's decently small. On the front, there's going to be a 1x1 bolt hole pattern. That's where the EVA tool is going to be attached to, and on the back is going to be the same 1x1 bolt hole pattern, and that's going to be attached to the mechanical swing arm that protrudes from the astronaut's head. So I'd like to go more in depth into how the actual mechanism works. So let that play for a bit. So the entire mechanism is split into two parts. The top half, which is attached to the EVA tool, is going to house both of the locking mechanisms, which is going to be the body tent and the snap action. And the bottom half is going to be connected to the swing arm again, and it's going to house the interface that interacts with the locking mechanisms. Now, the complete locking process is going to include you essentially have to guide the body tent mechanism on the top half into the bottom half. And then once that's in, you have to pull the thing in yellow, which is going to be the pin of the snap action locking mechanism, backwards. And that's basically going to act like a deadbolt on our doors. It's going to act like our secondary locking mechanism in case the body tent were to fail. And to unlock it, you do the complete opposite. You just push the pin forward and then press the red button on top of the T handle and then lift up. Now, I'd like to go more in depth into each of the locking mechanisms. So first is going to be the snap action locking mechanism. This is going to be the snap action locking mechanism. Again, the pin is going to be yellow, and we're going to have two PET G springs, which is going to be in green. What the springs allow is it lets the pin sit still idly because you need a certain amount of force to actually actuate the locking mechanism. So you can just lock it and leave it without having to worry about the pin moving by itself. And next is going to be the body tent. So whenever you press the red button on the T handle, it's going to move a rod downwards. And whenever the rod moves downwards, it's going to displace the two balls that protrudes from the mechanism inwards, which allows the rod to essentially clear a circular opening. And then to unlock it, you just let go of the red button, and then the balls protrude outwards. Now, I'd like to pass it on to Ethan for the analysis.
Thank you, Viet. Firstly, the linear snap action mechanism. This table gives the geometric, material, and loading parameters for a 3/8 inch 6061T6 aluminum pin that's under combined loading. Some assumptions include 40 pound-inches of applied torque and 50 pounds of axial tensile load, and this comes from operational analogs and EVA tool design heritage. And this represents a realistic worst-case scenario that accounts for off-axis handle loads as well as improper alignment. Setting the von Mises stress equal to the allowable 8 KSI and solving for the unknown shear stress, we get a maximum allowable shear of 137 pounds of force, which is more than the load capacity of 15 pounds. Next, for the ball detent locking pin, it summarizes the vendor-certified mechanical strength values. So all of these come from Harcourt's ball lock pin technical information data sheets. So using that information, solving for the axial force and dividing it by our factor of safety of 5, we get a design allowable of 115 pounds. And for the double shear on the ball bearings, dividing by the 10,000 pounds of force by our factor of safety, we get an allowable of 2,000 pounds of force. Here are our references. And that concludes our presentation. Thank you so much for listening.
So you mentioned that your device is incredibly small. How do you anticipate the astronauts being able to use it in their EVA suits with those large fingers?
So we had the constraint that it had to be in that volume of 5 by 5 by 5 inches. So that's definitely something we could look into, is trying to make the T handle bigger to be more optimized for the astronauts' gloves. Yes, sir.
I noticed your design has a lot of small, intricate, interconnected parts. Have you actually printed it and tested it to make sure it doesn't jam up in any way? Like if you rotate the shaft,
The only thing that we did print was the linear snap action mechanism, but we haven't actually incorporated it into the design. We just have the mechanism by itself.
And also, we want to consider for like future design considerations a self-correcting like geometry, so that even if it is slightly misaligned, it will correct itself along the geometry into the proper locking place.
All right, thank you, team. All right, next up, Texas State University, and the team name is Password Bobcat.
Good morning, everyone. We are the Integrated Camera Lighting System Hazard Detection Unit out of Texas State. What's that? Take a second right now. We're going to talk about this graphic. This shows the elevation changes in the moon. So these sharp lines you're seeing, that represents a steep slope, incline, or a crater, right? So all these present hazards that can trip up our lunar rovers. So that feeds into what we're trying to do here to support the Artemis mission. We need to enable hazard avoidance in extreme terrain conditions, like I mentioned, so steep craters, steep inclines, and large rocks. We need to operate effectively in dusty, low visibility environments, and we're choosing to do that using radar-based sensing. So the team is made up of our PM, Mr. Mason Smith, Zachary Gaiman, and Skylar Jamar, myself, Nicholas Humphrey. So again, this is straight from our PRD. We really make our beings here on this line that says you need to produce quality imagery. So what that means for us is sending out radar waves to detect and classify terrain hazards. We want to provide a graphical output for our operator to actually see what the radars are sensing. We want to integrate with the existing team, so we just want to snap in, not get in the way of what they're doing, and we want to be able to accomplish our goals. And like I said, we'll achieve this by operating modularly with this monster right next to us. So as you can see here, this is a high-level top-level diagram. So on the left here, that's our dev board, so that's the radar. Transmit and receive our waves, mix them. The data link down here, that'll basically box up our data, send it over to the brain, the Raspberry Pi. That'll run through spatial intelligence and pop that onto the interface.
Okay, I have the digital signal processing subsystem. It is responsible for processing those transmitted radar waves into three-dimensional coordinate points. This process starts with the transmitter antennas. These antennas are on the board. It'll send out a chirp signal, which is a signal that increases in frequency over time. It will be reflected off of an object, received by the receiver antennas, and mixed with the original transmitted signal. It then creates the intermediate frequency signal, or IF signal. Digital signal processing is applied to that, where it goes through a detection processing chain to produce our three-dimensional point cloud. This starts with the range DSP. It gives us a one-dimensional distance to the object. Then it goes through Doppler, which will evaluate the velocity of objects. CFAR will filter unwanted noise or non-hazardous objects. And then angle of arrival will give us a two-dimensional angular location. That combined with the range DSP, we get our three coordinates. You can compute the distance to an object by applying the Fourier transform to that intermediate frequency signal. Those peaks in the frequency domain represent detected objects, and the instantaneous frequency and phase at that peak can be computed into the distance. I have that simulated here in MATLAB for the range estimation. operating at the bandwidth of our signal, which is the chirp signal increasing from 60 gigahertz to 64 gigahertz. So the board that we use comes pre-flashed with the millimeter wave demo code. It is compatible with the visualizer application. Well, here in this image right here, it shows the point cloud that gets generated from the visualizer. This is the radar board picking up on an object maybe a half a meter wide in the field of view that is demonstrated in the diagram above that. I'll be using the visualizer application to create and test the configuration file, and then I will embed that file inside of the master subsystem program of the demo code. That way the radar is able to up configuration settings sent from the file embedded within rather than from an outside source. I will also be isolating those coordinate points that get generated from the detection processing chain. That way those data points get sent over to the Raspberry Pi to be displayed on the interface using our data link subsystem.
This is the data link subsystem. Like Nick was saying earlier, I basically just box up her points into a frame and then send it over to the Pi where I can put it in the point cloud buffer. This is kind of what the flow looks like, with the frame being made up of a magic number which starts the frame, a header which contains data about the frame, and then the TLVs, which is kind of the meat and potatoes of the frame, where it has, they'll say it's a float 32 and have the actual X, Y, and Z data, along with a CRC 32-bit check. That's a cyclic redundancy check to make sure that we maintain data integrity. The requirements are that we are underneath our specified baud rate, which we have said we need to put 500 points per frame at 12 frames per second to accurately detect hazards, and then we have the same frame on both boards, which is what the CRC 32 check is for, and we dispose of any frames that are altered. The next subsystem I have is the power subsystem. We're going to be powered by the previous team's power supply, which will supply 5.1 volts to the Raspberry Pi, which will then supply 5 volts to the development board and 5 volts to the display. This is our budget. We're budgeted 27 watts. Next slide. The way I'm going to test this is I'm going to do a no-load test where I don't send any current through the system, and then check to make sure there's the correct voltages at each terminal, and then a full load test where I send, just leave the system running and make sure that we never overshoot our 27 watt budget and that we don't overheat.
So I'm in charge of the spatial intelligence subsystem. Basically what we're doing is taking this point cloud from Zach, from the data link, and then each time we read a new point cloud, we also read from the parameters file, which we can then use to process the point cloud into detect hazards, and then push it to the render dictionary, which is a data struct that just contains a new colorized version of the point cloud, and then there's bounding boxes identifying the hazards, and then the terminal contains, it'll print measurements and data. So the main library that we're able to use is Open3D. Open3D gives us access to RANSAC and DVScan. RANSAC stands for Random Sample Consensus. This is how we're able to do our ground plane segmentation. Basically, taking 3 points, mapping a plane to it, counting the number of inliers within the threshold that's in the parameters that the operator can adjust. And then we do this 9 times, we can get a 95% confidence. And from this, the inliers, we pick the best one, the most inliers. The inliers become the ground points, the rest of them become non-ground points, and then the non-ground points we can take the signed points, so positive above ground, negative below ground, and split those into their own point clouds. For positive, we can do clustering. This is DVScan, density-based spatial clustering for applications with noise. We have a lot of noise. So basically what you do is you pick 1 point, count the number of points within an epsilon radius. This is all from the parameters file. And then you're able to build out a cluster. In this example, it's 10 points. You can start building out a cluster. And then depending on the size of the cluster, it's hazardous rock or known as hazardous. For negative points, for negative hazards, we don't have the data because we are prioritizing distance, so we don't get as much of an angle at like the bottom of the crater. So what we're able to do is we have to do it a little differently. We can't do clustering. We can quantize the points so that we can do less processing, and then we can fill in all the holes. This is the second plot, fill in all the holes with the ground plane equation that we get from Ransack, and then we can get a local maximum, smooth maximum, subtract the points, and then we can get the depth map.
So after all that, all the brain that Mason just described, the interface here, that's really the main goal is to provide the operator control over what the radar is doing. And that's done through tkinter, which is just a library available in Python, allows access to your sliders. But the main three that were chosen right now, like Mason mentioned, we've got the distance threshold, which just describes how strictly we're defining the ground plane. And we've got our neighborhood radius as well as the minimum amount of points. So the neighborhood radius, if you need it tighter for more, tighter investigation of whatever hazard you see, you bring that neighborhood radius in so you can see the difference in two rocks, which maybe it just appears one large rock, or you can push it out if you're not so concerned.
Overall, unit cost is $754. For semester 2, we plan on integrating our subsystems all together and then integrating with the main system. And yeah, we'll take questions now.
How are you getting sub 1 centimeter radius for 500 points? Because are you narrowing the field of view at all?
Where's that from?
If you take the half of the spherical area and the 50, you said a 50-meter radius, right? What is your how far do you measure to detect out your points?
So it's 30 meters out.
30 meters out.
Yes.
Okay.
Resolution is 4 centimeters. The 1 centimeter you may be getting from here is just it's an increment. So we're testing the interface, how much we can increment, making sure it's responding correctly.
Okay.
Anything else?
All right. Thank you, team.
Thank you all for your time.
All right, next up from UT, we have the Bevonauts.
All right, good morning, y'all. Thank you for joining us this far. We are Team Bevonauts. My name is Michael Harris, and I have here with me Javier. The rest of our team could not make it today, so sorry for that. And we bring to you today a concept for a lunar drone platform. And this is a challenging project. We've been working on it for 1 semester, and we will not have any more time to work on it. We're graduating at the end of December in less than a month. So the outline of this presentation will follow the background and the problem statement, as well as kind of where the design is currently. After that, we'll dive into the individual subsystems in depth, and we'll follow it up with an overview of our current prototype, tests we've done so far, as well as our future plans if we were to continue work on it. So the project background is nebulous at best. They've really not given us many requirements because they've asked a lot like right out the gate, and that's make something that can fly. So every other requirement after that is secondary, icing on the cake. We made it up as a nice goalpost to reach, but it's really, irrelevant if we can't make something that flies. So If we were to reach our requirements, hypothetically, we would like to hover for around 20 minutes, the duration of the average spacewalk or EVA. We'd like to be able to carry a camera payload to capture footage of these events. And we'd also like the drone to be able to autonomously follow its user to avoid any additional difficulties on the part of the astronaut. Obvious restraints. Lack of substantial atmosphere means we can't use traditional things like fans or rotors. We are left with very limited options in terms of propulsion. Propellants are also not ideal. That really leaves us combustion processes or non-combustion processes. And of course, we can't test combustion in a university laboratory. We've gone with non-combustion processes. That's the expulsion of compressed gas, specifically air. All right, currently in the industry, lunar exploration is not drone heavy. Of course, historically, we've had a lot of rovers, wheeled things that have problems with regolith and breaking down and being very heavy and requiring all kinds of power sources, such as the Apollo Lunar Roving Vehicle or Viper. More recently, they've tried branching out into aerial craft, with the most recent development being the Ingenuity helicopter, a Mars helicopter. This is a great development, better works in Mars atmosphere than the lunar atmosphere. Of course, there is Firefly's Blue Ghost, again, extremely costly, over $20 million per flight, and requires all kinds of propellant.
So looking at our problem statement, what is it that we're really trying to solve here? Lunar exploration, we're going to require something that is inexpensive, robust, something that we don't have to, interact with, can be hands-free, and can get off the ground. And so looking at, what we're really trying to solve today is creating a prototype that will solve all the problems within budget, of course, being able to carry a camera, so our load capacity is a little less than half a pound, being able to follow the user, and then being able to fly for at least 20 minutes. So going a little bit into our design overview, we evaluated various different concepts, about 5 or 6, and we really converged on a quadcopter style, similar to what you would see on a commercial drone, which uses nozzles instead of rotors to be able to get off the ground in the lack of atmosphere in the lunar environment. And so, as I said, it's going to be a stable 4-node design. This will be really helpful for our valve control system, which I'll get into shortly. The nozzles are going to be expelling compressed air instead of using a combustion process. This will be really nice because, compressed air is something that we know we're going to have access to in space, and so it's something that I think will be really good for a proof of concept to ensure that this is something that can actually be achieved. We're going to be using solenoid valves to control the output, so it's going to be either all on or all off. And we're going to use a laser cut wood body for the ability to use rapid prototyping and be able to try various different designs. And so some considerations to think about are the thrust to weight ratios. So we want to have something light enough to actually be able to push off the ground, and then degrees of freedom. So our solenoid valves, our thrusters are going to be pushing downwards, and so we don't have a lot of degrees of freedom for this, but there's definitely something we can explore in the future.
Okay, so diving into detail of our various subsystems, the primary one is the pneumatic subsystem. So how can we get air from our compressed air creator to a controlled place where we can decide how to distribute it in a controlled manner? So in our lab at UT Austin, we have compressed air outlets with barb fittings. So from there, we've just been plugging onto that with some kind of soft plastic tubing. After that, we have kind of an intermediate tank, a 2-liter bottle that's kind of acting as our containment device. Of course, that has a maximum allowable working pressure of about 60 psi. So it's at least something to work with. From there, we have a solenoid valve in line per nozzle. So each nozzle has its own solenoid valve, which we can operate electronically, turn on and off, again, to expel air. So a little more detail about how this is set up. Essentially, there are 2 tanks on either side of the prototype supplying 2 solenoid valves. So from there, we can distribute air to each nozzle in kind of short puffs or blasts. And so we'll kind of go into more detail about how specifically the solenoid valve control system works. But that's kind of the idea. On and off fast enough to create almost a steady flow.
Yeah, so talking controls, we're going to be using an accelerometer to measure the acceleration that is being imparted in every given direction. we're using specifically an ADXL 345, and so for those of you who know a lot about accelerometers, it does not have a gyroscope, so we're only going to be able to calculate the pitch and the roll that's being exhibited by the drone at any given time. And so calculating these values from the raw data, we're going to be controlling the pitch and the roll using PID controllers that are going to stabilize to something level. And they're going to be minimizing the error, ensuring that we're not falling out of the sky. And so you can see our closed loop here. So the accelerometer is going to be feeding this data back into the Arduino, which is going to be controlling the SolarWind valves and the nozzle output. Depending on how extreme that error rate is, there's going to be a duty cycle that's placed on the solenoid output. And so, you'll have something like 40% on, 60% off to kind of get like an average decrease in flow. So that'll be really nice because we only have all on or all off. And so this is something that we would like to see. This would be like a final design after more iterations, and we use like a light metal such as aluminum or carbon fiber if budget were to permit. We'd have our payload, our camera at the bottom, and then these 2-liter bottles on each side.
Okay, so jumping into our prototype, we have it physically in front of us. Here's an example of a few components that we used, but we'll move on a little more rapidly. Testing. So in order to test, we decided to measure thrust specifically, and we use this with this little load cell cartridge stand right here. So the load cell sits inside. We're blowing the pressurized air directly onto the face of the load cell to take a force reading. We're doing this because this is an example of the force that the table would see if we were trying to lift off from the table. Okay, and so again, this is kind of the flow of air that we're going for, so we isolated the entire compressed air system to take these measurements, and we're hoping to get at least 3/4 of a pound per nozzle of thrust. And here are some results for that, and you can see that we're drastically below the desired output. So this is not encouraging. Following another test, we were able to get a little higher by increasing the pressure to scarily close to our WAP. So do not try that at home. So maximum pounds able to reach about 0.11 pounds. Our Python simulation, of course, showed that in lunar gravity this might be a lot more feasible, but in Earth's gravity, unfortunately, we're still bound to Earth. For future work, we'll really need to conduct a body redesign in order to alleviate some weights. We have more of a skeleton design that we're hoping to iterate on and most likely 3D print. But again, this is future work for now. Future improvements in general, if we can increase pressure, we can increase thrust. We can increase area, we can increase thrust. There's a lot of changes that can be made here. We can have more control, we can have more degrees of freedom. We could always have more.
Yeah, so in terms of the control system, we could use Kalman filtering. So this is supposed to be an idea to better understand state space and tune our PID controllers to a better degree. So here are our references, and we'll thank you so much for your time, and we'll take any questions.
So, of course, air is a finite resource. So, do you have any ideas on how you would actually replenish your reservoirs?
Sure. So, there's always the problem of the drone having to carry the weight of whatever, fuel source or propellant source that it has. Ideally, we would offload that to the user. So perhaps the user is carrying additional air that can supply this, and the drone is always attached like an umbilical cord. Of course, it needs to follow the user anyway, so that's a possibility. But definitely, this idea, this concept, has a lot of deployment issues. It's a hard concept for sure.
What is your specific impulse that you're getting from your propulsion system?
No idea. Yeah, I could probably find that for you in the future, though.
Do you guys have any planned failure modes in case there is something that goes wrong with the drone? Like, let's say it flips, something bumps it, just an emergency shut off for the system, and an immediate evacuation or immediate and safe evacuation of fuel if stored on board.
Specifically for our testing, we would keep the caps slightly open as kind of like a pressure safety relief valve. So essentially the cap would go first on our like intermediate tanks. Obviously like full scale deployment would have its own set, would require its own FMEA, would require its own like hazard analysis. That's really, thinking far ahead in the future. For our testing purposes, caps would go first, which is the safest option for us.
Thank you. All right, we will take another quick 8-minute break and be back at 9:40. Take a seat, get started with our next session. All right, next up we have Prairie View A&M and Team Xenon.
All right, hi everybody. My name is Allison Armstrong. I'm the team lead of Team Xenon. This over here is Antavion Franks. He's my deputy team lead. This is Kwa Min. He is our energy conversions expert. This is Alyssa Stevens. She's our CAD girl and our energy conversion helper. And this is Jaden Best. He is our housing and landing guy. Our faculty advisor was Dr. Radhakrishnan, and our NASA mentor is Mr. Robert Knuckles. All right, so the Panther is a retrofitted X-Energy Zenith reactor. It's a high-temperature gas-cooled reactor that we have retrofitted for extreme lunar conditions and to power long-term future lunar missions.
Panther is designed for remote and limited infrastructure and equipped to completely decommission within 2 years.
Some of the key assumptions that we made when we were designing this reactor is that we mimicked the geometry. That plays a lot into how our testing went for this reactor. We also made our weight assumptions based off of the modularity and transportation methods of this reactor. Because it's possible to move it in a 40-foot high cube on a semi, we did a couple wheel configurations and figured out that it's probably not going to weigh more than 10 metric tons just by mode of transportation.
Our energy and performance output of our energy converter will roughly be around 3 to 10 milliwatts, and our structure of our reactor, our landing gear, and our energy converter should be factory assembled.
And materials, they should be corrosion, radiation, and oxidation resistant. Our reactor should reach around 750 degrees Celsius, and then we follow Zenith's safety and environmental compliance regulatory stuff, and then TRISO-X fuel utilization. Okay, we broke our project up into 3 different subgroups. So our core reactor team, our energy conversion cycle, and then our landing gear.
Okay, so this is our reactor. So that hole right there is where we put our isotropic fuel. It is replaced every 20 years. This is our energy converter. This right here and this right here are 2 Stirling pistons. And then this is our landing gear, which is our prongs are at a 45-degree angle for ultimate support.
All right, moving back to the core design basis, we did pick Zenith. It is a pre-existing high-temperature gas-cooled reactor. We picked a reactor to work off specifically because it takes years to validate a reactor from scratch. So this took a lot of time off of our thermal output assumptions and any neutronics or Monte Carlo simulations that we'd have to run. More specifically, we've thrown out this term a couple times. TRISO fuel is one of the main pivot points of our safety and our lifespan of our reactor. So TRISO fuel is really cool. It's a high-assay, low-enriched uranium fuel. It is TRISO, which stands for tri-isocarbide. It has a silicon carbide, a pyrolytic carbide, and a porous carbon layer. All of those go into the shielding around individual uranium kernels within the fuel kernel, the fuel pebble, itself. These carbide coatings provide a really, really high melting temperature. Silicon carbide specifically melts at 2,700 degrees Celsius, which is higher than the reactor temperature itself can get by itself. So, in theory, the reactor will not melt down. The other carbon layers are to provide insulatory shielding to that silicon carbide layer so that it doesn't crack and cause any issues within the fuel pebble. These layers combined provide a lot of protection against our really high energy emissions that are coming out of the fissile reaction at 70 to 100 mega electron volts. 90% of these particulates are stopped by the free fuel zone and the pebble itself. The ones that don't get stopped by it are lower energy. We're looking at alpha beams, proton beams, and recoil things, which we did test for. So we did our shielding validation and TRIM, which is another acronym. It stands for stopping range of ions in matter and transport range of ions in matter. We did 10,000 ion simulations in a monolithic boron carbide layer at 0.03 centimeters thick. We kept it really thin because boron carbide is a ceramic. It's really fragile. It's really sensitive to thermal gradient pressure causing cracks. It's really sensitive to expansive gases causing cracks, and the thinner it is, the more resilient it is. And as you can see on our damage profile that we have up here, the ion activity, the damage is not transmitting through our shielding, so it is effective at the width we chose.
Okay, we calculated thermal validations for several key stages. So helium, core, lead, boron carbide, and then space. So then some of the parameters, so the core thickness is 0.05 centimeters, the lead thickness is 0.02 centimeters, and then the boron carbide is 0.03 centimeters. And then we use, some of the formulas that we used were Fourier's law for heat conduction, and then we also used the heat equation for the transient conduction, where we use derivatives and stuff to calculate it. Okay. We utilize MATLAB for some of our graphs. So as you can see in figure 1, the temperature across layers represents the temperature distribution from the helium side to space at 5 different times. And then graph 2 represents the temperature envelope that represents the minimum and maximum temperature between 0 to 30 seconds.
So the high temperature thermal energy is then fed into two Stirling engines, which act as the main electrical backbone to our whole system. So this generates enough electricity for our main power bus, which includes communication, in-life support, and all the electronics, while the onboard batteries manages start-up demands. We also have the dedicated dump loads to protect the reactors by absorbing all the excess power, just in case that the primary loads disconnect, to ensure safe and continuous operation under all conditions.
Okay, so our Stirling converter is high efficiency, long-lasting, space-issue converters. Our sodium heat pipes are continuous in supporting our helium reactor, in the sense of that it can support it with heat transfers for numerous years. And our Almini heat pipe fluid is one of the best fluids for low temp radiation, in the sense that it has free thaw capabilities.
Okay, for the landing, what we decided to do is we had to have it more like a capsule look, and with the bulkhead at the outside in order to mitigate the dust, the lunar dust. In a way, we also had to deal with all the constraints and the issues, is that we used multiple materials such as carbon polymers, such that they were the lightest out of all the materials, and they were actually the most durable with carbon fiber reinforced polymers being the best. Additionally, we used titanium alloys, specifically aluminum 6061 T6, as it was the best material used in order to project lunar dust in order to make calculations. Additionally, with dealing with the thermal heat, we used carbon-carbon composites, as they gave an acidity of 0.9 with the temperatures. Additionally, used a structure that was more similar to like a tripod, as with the 40, as it can be retractable up to 45 degrees, and ensure that when the reactor does land on the surface, it doesn't crash or in fact or cause any more issues in regards to lunar dust.
All right, thank you so much for listening to us, guys. Here's a QR code with all of our references and a little bit of contact information in case you don't get to ask a question now and want to ask it later. We'd like to open the floor to some questions now, though.
You mentioned that you assume that the sky is 3 degrees Kelvin, but did you consider that only half the sky is visible when it reaches the radiation calculations, and half of the surroundings is the ground, which is much hotter?
Yeah, actually, we were considering mostly, as far as our thermal diffusivity, that our Stirling engine could stall. Stirling engines can handle overclocking and overheating a little bit more than they can handle getting cold. If it gets too cold, it stalls and we stop producing energy. So our main validation was that we could keep a continuous source of energy going, so we focused more on proving that it lasted cold over hot.
I'm talking about the heat transfer in and out of the system.
Can you repeat the question? I'm sorry.
So you mentioned that you assume that the surroundings is 4 degrees Kelvin, the cosmic microwave background. But did you consider the fact that half of the surroundings is included by the moon, which is at much higher temperature, reducing the amount of heat you're able to move away? And what temperature did you use for the moon, essentially?
What temperature did you use for the moon?
Yeah, I kept it at 3 kelvins. That's what I assumed.
We didn't make any extra assumptions off of that. We really wanted to prove against cold over against hot.
Yeah.
Yes.
Could you explain how those 3 different parts of the reactor work together? Like, I don't understand how the 3D printed things you have on the table, how do those relate?
Oh yeah, absolutely. They're not printed to scale, so this is a lander at a very much smaller scale than any of the other pieces. We printed them as we could get them out. So this is going to be our main reactor system. We have 2 different vacuum seal purge systems to load fuel casks in and out of our system. The main pebble bed we represented right here. And on top of that, we would have a energy conversion cycle, which would stack up to where we vent all of our superheated helium to a heat exchanger that powers the Stirling cycle. Ideally, all of this would fit stacked inside of the landing gear. I don't want to break the legs.
All right, thank you, team.
Good morning, we're Team Farscape. I'm Connor Anderson, the team lead. My teammates are Kyle Cavazos, William McBrayer, Diego Regalado, Marcus Martinez, and Zachary Davis. We're building a machine that'll bury fiber optic or power cable in the moon. Why is that important? Well, we want to establish a long-term human presence on the moon eventually, and it's going to require a lot of infrastructure, habitats, scientific equipment, LTVs, things like that. All of that requires power and communications. We can't just leave power and communications cable lying all over the surface, because if an LTV drives over it, well, bad things happen. To do that, we have to define the depth into the regolith that the cable would need to be buried in order to keep it safe, and make it reasonable for a machine to bury it without being overly complex or, frankly, just too big to conceivably launch and land on the moon.
To clarify our overall objectives we want to have for this machine, we would at least like to bury cable 1 meter below the lunar surface at a rate of 5 meters per minute. That is a hefty ask, but we're trying to achieve it. We're also trying to make it very easy for the astronauts to work in their bulky suits to service it, change out the cable spool, and hopefully to have a very long service life so they never have to worry about ever maintaining it or ever having to replace damaged parts.
When dealing with lunar equipment, there are obviously some major design constraints. Some of these constraints are due to the moon's lack of atmosphere, like the radiation and the extreme temperatures our rover will have to endure in a low gravity environment. Some other constraints are due to the moon's surface, the moon's regolith, the uneven terrain, and the abrasive dust particles can cause wear and tear to our mechanical components. And we hope that our rover will have a long service life and have a usable power supply.
Yeah, so the lunar environment is the main difference from anything that was on Earth. So the lunar regolith is made up of fine dust and rock fragments that are extremely abrasive and electrically charged from UV radiation and solar wind. And because of this, they can stick to the equipment and potentially cause damage. And the density at the surface is 1.3 grams per centimeter cubed, and that increases with depth. So at our 1 meter, it'll be around 1.83 grams per centimeter cubed. And that is found using that equation. So the gravity is 1/6 of the Earth, and that is going to affect the dust. When we trench it up, it won't settle right away, so it can get on our machine. And then the extreme temperature change is from negative 130 degrees Celsius up to 120 degrees Celsius, so that is going to be a determining factor in what materials we use.
We designed conceptual models for our functions mean chart, and we focused on our primary functions and the means to achieve those functions. We then added our constraints to our functions mean chart to get our conceptual design. And our conceptual design consists of a 1 meter long laboratory plow, a track system for uneven terrain, and a compact geometric box for lunar regolith, so it keeps up.
So the most important part of our machine is going to be the trench and how we cut into the regolith to bury the cable. And so to do that, we are using a vibratory plow. And what that is going to be a long, slender metal blade that extends off the front end of our machine. And then is attached to a high-frequency vibratory box that then allows the blade itself to vibrate at a high frequency to then make it easier to cut into the regolith. As it moves forward, if you had a static blade, there would be a very large moment that is occurring onto the machine, and it would cause it to tilt. So then using a vibratory blade, that allows it to push through the regolith a lot easier without needing as much force from the machine as much power. With this system, the cable can also be laid at the same time, either using the vibration of the blade itself or a secondary system like a powered system to push the cable down into the soil. This also is a trenchless system. So instead of having a wide trench with a lot of dirt that gets kicked up and pushed off to the sides, it has a minimum amount of dirt that actually gets piled up on top of it, requiring very little backfilling to go back over that trench and repack and refill it. So the current design is inspired by pre-existing designs that are used here on Earth in very similar soil environments like sand and silt, and even down to about the same depth, around 1 meter. Total length of this blade is found with that depth over the sine of the cutting angle, which is 23 degrees. This angle is found to be a good angle to be at, to not have a lot of force acting upon the machine, but then also having a good amount of cutting length along the blade. The thickness is going to be about 0.06 meters or 6 centimeters wide. That's going to be about twice as wide as the largest cable we are presuming to be using. And then the entire shape of the blade is more of a wedge to help push that soil off to the side, and then also drag it upwards as it moves forward. And then the very bottom of it is going to be at a slight angle to help keep the blade at the appropriate depth, so it kind of scrapes along the bottom of it, so we don't cut any deeper than what we have to be.
Moving into our second semester of senior design, we're going to continue to refine the plow design, as well as test materials with FEA, and ultimately produce a hopefully nearly fully functional model at about 1/6 scale that we can test using simulated lunar regolith in a lab. We'd like to thank our faculty advisors at TAMUC for all their help throughout the semester. our NASA advisor, Mr. Lansdowne, and everybody at Texas Space Grant, and we look forward to working with you in the future. Questions? Yes.
So what kind of challenges have you guys faced or plan on tackling when it comes to the differences between lunar regolith and Earth-based regolith?
The biggest thing with lunar regolith for us is having it get stuck to the machine and find its way into some of the mechanisms. Because once it's there, it'll just shred everything. No matter really what material we make it out of, it will cause premature wear and ultimately fail apart.
With the, I guess, blade part only being, I think you said 6 centimeters thick, what materials were you thinking about making it out of? And then, like, how would you address just, like, bending a rock or something like that?
We haven't currently defined a specific material. We're going in between a few different alloys. Initially wanted to go with something fairly hard, but we're worried about cracking, especially when we get into like a lunar night scenario where at that extreme cold temperature. For rocks, we're not very concerned about small rocks. We should be able to push them out of the way without much issue. If we do hit something larger, that's where having a powered spool feed's going to come into effect, because we're going to have to back up and have it rewind and then go around. But we're hoping that we'll be able to avoid most of that. Yes?
So if the problem with regolith is that it's going to tear up the inside, how are you guys planning to mitigate that risk?
That's one of the reasons we chose the vibratory plow, is to reduce the possibility for ingress of that regolith into our mechanisms. So with the plow, there's really not a ton of moving parts for the regolith to find a way in, and most of the wear is going to be focused on that plow blade, which is why we're focusing on the material selection right now.
Thank you, team. All right, lights, camera, Bobcats.
Good morning, everybody. My name is Colin Peters. These are my teammates Erica Griffin and Jonah Hartley. And together we built the Integrated Camera and Lighting System, or ICLS. So for a lot of very, very cool... So for a lot of very, very cool reasons, the moon presents a very unique lighting challenge. It's an ultra high contrast environment, meaning it's hard for cameras to grab images without washout. So our project tasked us with creating a system suitable for a lunar surface rover that would facilitate quality imaging. Our goals were to support a rover traveling at 4 meters per second, and we wanted to dynamically provide near uniform lighting to a scene to avoid camera washout, all while enabling the operator to focus on the mission at hand. To tell you about how we achieved some of these goals, Jonah's going to take over.
All right, thank you. Our solution focused on 2 main goals: mission safety and efficiency. I'm going to quickly touch on 6 of our features that support these goals. This figure is the core of our project. It shows how the view of a lunar rover is handled by the lights. By Cutting our scene into sectors, we built granularity, allowing our lights to hit specific shadows without wasting energy casting light across the entire scene. And then by ensuring that each sector is illuminated by at least 2 lights, we build redundancy. To achieve this sector map, we designed a single modular light column and then implemented 2 of them to our frame. You can see that each of our light columns have their own connection to our drive box and their own independent drive electronics boards. This design improves scaling, lowers integration risk, and improves equipment sparing. To control these lights, we have designed an automatic and lighting modes. Under normal driving conditions, the project should be able to automatically remove shadows from the scene without prompt from the driver. However, in many situations, an astronaut might want to override this manual automatic mode, and so we have implemented a manual control board. Our system is also able to send high-frequency signals over long distance. We are currently sending a 2 megahertz clock signal 6 feet down to our drive board. Without this system, we experienced extreme signal smearing and significant amplitude loss. However, by sending on an RS-485 standard, we're able to remove these issues and allow our design to fit into a greater variety of lunar vehicles. Our system has 3 cameras, a lighting analysis camera and 2 HD cameras. And the 2 HD cameras are designated for lunar day and lunar night based off their dynamic range. Having 3 cameras also improves our redundancy because if 1 or even 2 of our cameras fail, we're still able to record the mission. We also have thermal management system. If this system was going to the moon, it would require far more robust thermal control systems. However, here on Earth, our prototype just needed to not overheat. So we implemented 4 major thermal control decisions. We have all of our drive electronics in a ventilated box with fans. We overspec our sense resistors. We have individual heat sinks on each of our power FETs, and we installed the second board to the lid of our electronics box rather than stacking them to improve airflow. And finally, we have a backup battery. If you're driving on the moon, you need emergency power. So we implemented this using an uninterruptible power supply and then integrated an emergency power mode. So when driving on automatic mode, if main power is lost, all the lights will switch off except for our low flood. And that's because this light behaves like the low beams on your car. Our system is then able to report the battery charge and the estimated runtime based off current power draw to the user. I'll now pass it over to Erica for a deeper dive into how it works.
So all these systems come together and give us our overall system, which you can divide up into 3 major parts: our power, our electronics, and our software, which act as our heart, mind, and arms of our system, allowing us to interface with and control our scene. The eyes of our system is our lighting analysis camera, which we massively improved on from the previous semester. Before, we were grabbing an RGB image from the environment, converting it to the HSV color scape, isolating the value channel, and creating our pixel maps based off of that. Now we have a nice monochrome camera that grabs luminance values directly from the scene, and we can use that luminance value and threshold it to determine how dark a sector is. That threshold is very important for us to define correctly, as if it's too low or too high, it can consider all the sectors to be always bright or always dark, but we also need it towards the lower end of our values in order to be able to distinguish black from shadows. We also learned how to do some image smoothing so we can capture an image from our environment, and due to the motion of the camera and the changing environment, there's a lot of jittery noise originally just due to changes in pixels. So adding an exponential smoothing curve allowed us to really control a lot of the noise and oscillations we were seeing in our lights in the previous semester. For our code, we're running Python on our Raspberry Pi 5, and it is a very generic loop that will simply check all of our states, if it's in emergency mode, non-emergency mode, which camera we're using, if it's a day or night camera, and if we're in auto or manual mode, and it'll check the values, show the display, overlay information to the user, and then continue the loop until prompted otherwise.
So once we had all this set up, we faced a really, really big question of how do we control this? And so to approach that problem, first we began with system identification. We needed to quantify how our system responded to how we changed the lights. So we used a pseudo-random binary sequence to determine that, which is a very fancy way of saying we turn the lights on and off at different frequencies and just observe the changes. Then we used some curve fitting tools and some system identification wizardry from MATLAB. They have an amazing tool suite for this. And we found a model that fits our system very well. It's an autoregressive exogenous model, which is a fancy way of saying it's a discrete difference equation where past states shape the outputs. And so we found on our training data that we had a very good fit for the model, and then also on our validation data sets, we found a tremendous agreement, giving us confidence that this was an accurate characterization. Then, using MATLAB's PID tuner suite, we were able to start designing a controller. So it's amazing, it gives you the parameters for the controller, but it's not exactly for us one-to-one. Our system was slightly different when we were using the test code versus our real loop. So this was sort of a way to ease us into the controller design and didn't give it to us right away. So we had to tune our controller a little bit, and once we did, we had tremendous results. So we found that our system can respond, and it can recognize a shadow and respond in about 2 loops of code, which corresponds to roughly 200 milliseconds. And our time to rise in that period, when we ran it, this is in nighttime conditions where we had all the lights off, it got dark, this is the sector brightness, and then once we engaged auto mode, our time to rise, which we defined as the time to reach 90% of the final value, was under 750 milliseconds for most runs. And also, our time to settle was less than 1.25 seconds. And so we thought that that supported our goals of can this be used to light a scene for an operator, and can it facilitate quality imagery? Additionally, there's a tremendous amount of potential for energy saving. This is a similar condition, and in the interest of time, I'll just sort of point out. Here, what we have is this is our PI controller naturally responding to an overdriven scene and dimming the lights where it's not needed, saving energy. And so although we love the response of our system, it's not perfect. And so our measured data indicates that we have a severe amount of crosstalk from our lights. The floodlights specifically are a huge problem, and that creates a coupled system where one light is influencing the sector of another light, which is not ideal. Future work, I think, should strongly start there. We need to decouple these systems using optics, and we've designed a parabolic reflector and lens that we think could work, but it needs to be manufactured, tested, and integrated. And even then, no optics system is perfect, and so a more dynamic control scheme, like model predictive control or another MIMO, multiple input, multiple out controller, we think could be good. And we laid the foundation with our system identification for a model predictive control scheme to be implemented, but again, that's something for future work. So we'd really like to thank our NASA sponsors, Ms. Tony Clark, and our faculty advisor, Mr. Jeff Stevens. And there's a ton of other people who contributed to this project, and without them, it wouldn't have been possible. So I'd like to open the floor for questions. Yes.
So your device has a lot of cables and different operating systems. Have you guys thought about lunar regolith and how that might negatively impact your system and potential mitigation strategies?
That's a great question. And so we focused a lot on the junction points. And for us, that's why we have, our Amphenol connectors have, they're keyed and they have an actual twisted lock. So those are sealed. So there's certain, parts of it that we have considered, making sure that it's not only just sealed to the environment, but that it's also robust and vibrational actions won't, shear forces won't affect it or pull it apart.
Thank you.
In the back, handsome gentleman.
So you have a day and a night camera, and I think what you said is that each camera has a different dynamic range. Was that correct?
Yes, that is correct.
What's the benefit of having two cameras with different dynamic ranges as opposed to using one with a higher dynamic range and then having exposure correction?
Great question. So we spent a lot of time looking and thinking about how to take quality images, and what we found is that the range on the moon's surface, it's so large in terms of the light that's provided from the sun and the shadows because of the material conditions of the moon. No atmosphere means that light is collimated. So very interestingly, what we found out is when we have a scene fully lighted with our system, so say we have all of our lights on, and then you encounter a patch of sunlight, that difference, the dynamic range between those two min and max values, is actually less than a shadow and when our system is fully lit. So in order to, we were looking at cameras that could handle that type of range without some sort of washout, and they were, you know, hundreds of dollars, if not thousands of dollars. And so we sort of took a step back and we said, well, what if we just found cameras, maybe a night imaging system that's a little bit more suited for shadows, and then something with, you know, a higher HDR type setting. And we took a 2-camera approach because then we thought it also emphasized this redundancy aspect.
Thank you, team. Okay, we will take another short break and reconvene at 10 minutes after 11. Okay, please have a seat. We'll get started with our last session of this morning. Okay, good morning. From UT Arlington, we have Team Nan.
All right, good morning, everyone. We are Team Nan from UT Arlington, and this is a conceptual design and analysis of a Follow Me camera drone. This is our team. Our faculty advisor is Dr. Wayne Wong, and our NASA mentor is Chadwick Lansdowne. A little background on our challenge is we have astronauts going back to the moon, and their time is incredibly valuable. So can we have a system in place, a drone in our case, to carry a camera and record their activities autonomously? And there are several challenges, primarily the lack of an atmosphere and how we're going to do that propulsion method. So I'll hand this off to Nashwan.
Thank you. For our market research, we learned that we got inspiration from each one of the missions. From the lunar lander, we learned that hyperbolics are very useful for propulsions. And then from Firefly Glucose, we learned how COTS could be really useful for our challenge. Both the system uses bipropylene fuel mixture, which from where we also got inspired by, and also uses a bipropylene mixture in our Follow Me camera drone. Here are our design requirements. We must have a camera. It has to fly for 20 minutes, use the lunar environmental constraints, and must have a stable position for its imaging payload.
The first challenge that we faced was the thermal issue. You see, without an atmosphere on the moon to stabilize the thermals, the temperature fluctuates wildly from negative 260 degrees Celsius to about 121 degrees Celsius, according to the NASA data sheet. Because of this, the radiation that we're able to achieve through the drone is very, very small, especially compared to conduction or convection. So as such, we have to reduce the amount of heat that we absorb through the sun by using a combination of retroreflective coatings and paints in order to reduce the amount of heat that we absorb. So we ended up settling on AWZ white paint, which is standard for a lot of NASA missions to handle the steady state. Then after that, we considered the propulsion. The main form of propulsion typically used in a vacuum is rocketry, where you use the conservation of momentum in order to create a force by expelling gases. And we modeled this, depending on the type of flow, with two different flow models. In short, basically, the more mass that your propulsion system needs typically means that you need more mass for the propellant and so on and so forth. So in order to reduce the mass ratio, we want to increase the efficiency, and to do that, we want to maximize the exhaust velocity.
Another point of consideration was the composition of the lunar regolith. This is important for our future ISRU things that we'll talk about. What we were able to find is that the moon is mainly made up of inorganic oxides, and that there are very few compounds of water and organic compounds. Another thing we considered was non-rocket propulsion. None of these were.
For our non-rocket propulsion methods, we had steam, compressed hydrogen, or regolith, which cannot qualify since they required high tank mass and insufficient performance for convergence. Here we can show that the propulsion system that falls under the red zone is non-convergent. That means it has a low thrust to weight ratio, and for which is why we cannot use electric propulsion as well. And for our nuclear thermal, it has a lot of high thermal strain on the tank, which is why that gets disqualified. Next, we switched to rocket propulsion methods, and we considered HTP monopropylene and solid propylene, along with chemical bipropylene, but the other two had low thrust and serviceability issues, which is why we went with chemical bipropylene, as it provided a higher thrust than all of the other propellers.
In terms of oxidizer, the one we went with was liquid oxygen. We chose it because of its high performance and high density. The only issues was it required a complex system to store and use. Additionally, for our hypergolic fuel, we went with silane. It's because it is a silicon-based fuel, which means we can synthesize it on the moon, and it is pyrophoric, which means it will react in the presence of oxygen, which simplified our combustion. For the silane synthesis, we were able to do it using this chemical process. The main point is we would need the silicon dioxide from the lunar regolith, as well as some sort of hydrogen input. In our case, that could be either hydrochloric acid, or we could get hydrogen gas through water electrolysis from the polar ice caps. We also use NASA CEA tools to find a number of important fuel characteristics, the main one being the oxidizer to fuel ratio, as well as thermodynamic data.
So in order to determine the mass of the system, we took an iterative approach using the rocket equation. We began with the camera load as our mass, and we converged upon a value of 8 kilograms. Now, using our analysis in MATLAB, we see that a higher fuel density is quite useful for us because that reduces the radius of the tank. And also a higher pressure inside the tank would increase the wall thickness to address that. So we need to meet a sweet spot between the two. So based off of that, we used a condensed propellant in order to maximize the fuel density, and that resulted in a boil-off due to the temperature difference between the ambient and inside temperature. This simplified the combustion in the injector and allowed us to utilize the heat absorbed by the spacecraft to improve the work output. When we ran this mass optimization procedure, we found the smallest possible wet mass was achieved at 3 bar of chamber pressure. And now to the actual tank configuration. We start between a spherical and a cylindrical tank. Now, spherical tanks have half the stress experience in it compared to a cylindrical tank. Therefore, we went with that. And to reduce mass, instead of having 2 different tanks for the fuel and the oxidizer, we combined both. So on the top we have silane, and on the bottom we have liquid oxygen. These are separated by a diaphragm, which is able to expand when any gas, an inert gas, is pumped into it, pushing each of the propellants into their outlet valves.
So the diaphragm design was done in consideration with the low temperatures that we experience. We used a neutral stress state halfway between the burn to model the neutral state of the diaphragm, and any additional deformation and curvature was added onto the stress to determine basically how much flexibility we needed. We chose a Teflon, a fluorocarbon, which, due to the limited amount of range of motion, we believe would be flexible enough, but we want to test this out with a physical experiment as well.
With all that being said, this was our final drone model. It has the bipropellant tank with the diaphragm as previously mentioned. It has the camera to fulfill the design challenge requirement, and we went with 6 thrusters. We went with 6 because we did not want to use linear actuators, or not linear, just actuators for simplicity, as well as meet the minimum degrees of freedom.
We designed our controls. We designed a control system that modeled the dynamic response that the drone would experience on the moon. While 5 thrusters would be sufficient to control all 6 degrees of motion, considering the gravity vector as well, we chose to go with 6 because it allows us to have a symmetric pair of thrusters that would impart no net moment onto the vehicle for a stable hover. Then we reduced the first order response instabilities using the first partial derivative and validated our configuration using the controllability workflow in MATLAB. For our thruster design, we started with first order principles and combined our transfer function and fit our dynamic response to the data that we were able to find online to create a transfer function that we use in our dynamics model to make sure that our control system would realistically be able to control even with the inaccuracies with the thrusters. And the thrusters were modeled and dynamically tuned to using CISO tools in MATLAB, but we didn't have time to fully implement the guidance system for the simulation, which we want to do in the future.
So in the future considerations, we'd love to actually make a physical model of this, or at the very least a virtual model. And what we would really like to do is make sure the diaphragm, the material we choose for it, can expand under the cryogenic temperatures that the propellants are exposing it to. And we believe that this drone could be equipped with scientific experiments in the future, or perhaps some kind of transport capabilities. So on that note, thank you for listening, and I'd like to open the floor to any questions.
is your estimated flight time for this drone?
20 minutes.
20 minutes.
And it meets exactly the design requirement as outlined.
So you said the diaphragm will basically expand and push out the fuel into the nozzles, basically. How
Yes.
would you control that to where it mixes the proper ratio for the oxidizer and all that for the propellant?
Valves. It's purely valve control. All we need to do is inject the fuel into the combustion chamber, and since the propellants are pyrophoric, they will react.
Not sure if you like addressed this or not. So could you give like a theoretical cost for this?
A theoretical cost?
I can go for this one. So the theoretical cost is highly dependent on both the transport to the moon and how much you're able to create the fuel at the moon itself. So our fuel choice was designed so that we can maximize how much of that entire reaction can be achieved on the moon. Transport, we would require, about 12 kilograms of hydrochloric acid to be transported at least once, and that would give us about 6 different flights per refuel from Earth. Using an estimate of about $2,000 per kilogram transport from Earth to the moon, that's how we ballparked that initial cost. You want to talk about the reaction?
So once we have that initial fuel up there, including the hydrochloric acid, this reaction assumes that we will lose about 15% of what we put into it every time we run it. So it's not like a 100% thing. You can't just run this infinitely and just have infinite fuel. That's not realistic. But we assume that after around 6 flights, you will need to send up another mission to refuel. Yes.
All right, we have to cut off, so thank you, team.
Howdy, I'm Brian Parks. I'm Caden Smith. We are Army supporters from Texas A&M University. We're participating in the Human Nano Challenge, specifically the fluids transfer between surface assets. And this is our flow solution.
So for some background, there are high delta V requirements to go beyond low Earth orbit, and this means that we need to bring a lot of propellant. And the problem with this is that this reduces the amount of payload mass we can take with us. And this high upfront cost deters stakeholders from investing their time, resources, and money into establishing a greater human presence beyond low Earth orbit. So a team at our school, we're working on creating a lunar railroad solution that essentially makes a railroad that links different surface assets on the moon. And so this is to help establish greater human presence on the moon. And this is propped up by the fact that lunar regolith is high in oxygen content. And so by using molten regolith electrolysis, we can separate the oxygen from the other minerals in the regolith, and then we can take this oxygen and condense it down into liquid oxygen. And this would mean that we would have oxidizer on the moon, which then we could transport to geotransfer orbit to allow for refueling both in geotransfer orbit and on the moon's surface. And so the overall development of this project it is meant to scale up to processing hundreds of metric tons of lunar regolith. And so with that in mind, we have all this oxygen, but how we're going to transport it is the issue. So on the lower ends, this is meant to continuously produce, like the molten regolith electrolysis is meant to continually produce liquid oxygen. And so on the lower end, we would need to transfer about half a metric ton a day. And on like higher, or whenever humans are present on the moon, which will be about every 2 years, there will be a time span of about 10 days in which we will need to drastically ramp up how much we can transport liquid oxygen in order to fill the landers. And so this is why we're focusing on surface-to-surface asset transfer. And so our objectives are that we will efficiently transfer liquid oxygen between CLPS lander, its liquid oxygen storage, to a human lander service. And then also we want to transfer oxygen between the reactor and the train liquid oxygen storage, and then from the train storage to a launchpad storage system. And these is to establish fundamental designs that are scalable for their requirement phases. In this interface diagram, what it is, it describes the relationship of fundamental proof of concept for this, and we would only have to transfer about 30 kilograms of liquid oxygen on the low end per day, which is assuming a very high yield, so realistically it'd be even less than that.
So as mentioned earlier, so this is our proof of concept, low MRE, where pretty much we're going to land a lander on the moon, and we're going to produce a small scale liquid oxygen and store that until a Starship lander arrives and just verify that all this technology works. But as mentioned earlier, we're going to primarily we're going to be working on trade studies and working on models to we're going to develop models to verify certain designs. So like there's certain considerations we have to look into when transferring fluids on the moon. Specifically, due to the lower lunar gravity, the surface tension plays a more prominent role relative to than we have on Earth. As a result, that influences how fluid is transferred and causes issues with laminar flow. So we're looking into surfaces that have the most surface energy so that those influences are minimized. One major consideration we have to look into is dust mitigation. Because we're transferring between different surface assets and not like, within a specific tip standard, we have to consider like, okay, how are we going to prevent dust from entering our fuel ports? Because if we're docking these assets like the train to a launch pad, if dust gets inside our fuel, that could compromise a rocket or compromise our own systems. So we have to find ways to minimize dust from influencing our systems. We have to work. Our system needs to be able to operate for at least 2 years. We picked 2 years because that's the at least for the initial Artemis missions. That's the time difference between landings. So we want our landing to ideally work. We want our system to work beyond 2 years, but at least 2 years in case it's an issue. And we need to make sure LOX remains in a cryogenic state, in a liquid state, so that we can easily have fluid transfer without the LOX turning into a gaseous phase. And we're considering all these in our trade studies. Further developments, we're working on a model that would take these things into consideration. We're currently doing the trade studies, and once those trade studies are completed, we're going to create models based off of those solutions, with the idea that based off the results from our model, we can better inform our trade studies and iterate on our designs. There are certain assumptions we're going to do initially. We're going to keep the model simple by using just like horizontal pipe with all the bands and curves, and we're going to use the constant pressure and temperature, but eventually we want to build up from this and better inform our designs in the future. As I mentioned earlier, we're working on trade studies for specifically the material cooling within the cooling within the transfer pipes and the pipes themselves. we're going to revise any discrepancies within our comps, and we're going to prepare methods to verify amounts. Thank you to Dr. Dunbar and Mr. Singh for advising and consulting us on this project. Thank you for the rest of the Armis Rail team for helping with some of the preliminary research and figures. And thank you all for listening.
How do you plan to post-process your CSV models in order to get useful data about the effect on the pipes?
Like how we're going to take it, how we're going to verify the
procedure.
We haven't gone that far. We're mostly working on what our assumptions are. Like we're working on like what assumptions are going to put into our model to make sure it can work.
So what have you actually achieved?
We have worked on con-offs. We're working on like the inputs replacement for the model, but we haven't gone to that point where we actually have a full model built.
Any other questions? All right, thank you, team.
Yeah? All right. My name is Julian Garcia. This is Byron Hernandez. This is Michelle Marquina, Tangina Islam, and Rowan Brumant. And we are Team LENS, also known as Lunar Exploration Navigation System. And our project is the Integrated Camera Lighting System Optical Optimization Project here at the Houston Engineering Center. So a little bit of our backgrounds. Cameras are vital for space and lunar exploration, obviously. Quality of images depends on the poor illumination as well as the camera exposure balance. Integrated lighting and camera system often uses modern programmable lights and cameras to adapt to various lighting and surface conditions in space. And NASA uses such systems for autonomous piloting as well as spacecraft operations.
All right, so as you can see from these images, lighting can vary a lot on the moon. There's these really dark, deep shadows, and then also in contrast these really bright areas. So pretty much the goal of our project is to try to mitigate that so we get better quality pictures.
So our major problem statement is the current lunar imaging system produces inconsistent imagery due to the various lighting and its fixed setup, which it cannot adapt to the changing conditions, limiting their image quality as well as the usability. So there's three major problems.
Like I said, inconsistent imagery due to the varying lighting conditions, and a fixed system can't adapt. So pretty much our goal is to create an adaptive dynamic system where the lights are able to adjust based on what the camera is picking up on ground. Another one of our goals is to design a mechanical mount that is able to support all our lights and cameras, and develop an algorithm that is able to adjust the lighting intensity to the varying lighting and surface conditions.
So how does the project work? Essentially, we're having a rover that's going to be moving continuously, right? So it's going to be continuously capturing images at a certain frame per second. We're going to take images, and then from there, our algorithm is going to analyze whether we either need to reduce noise or adjust for brightness based on what our algorithm says as we evaluate the brightness conditions. From there, we will reach target brightness values. And once they are reached, we will obviously receive a nice, sharp, well-lit image depending on what the algorithm has assigned. From then on, the rover will continuously keep moving and keep adjusting for images and lighting conditions.
So this is the flowchart for our system. So first, the camera will capture the image, and then based on the image's darkness and brightness, the controller will make adjustments, and then the camera will retake the image, and then the loop will continue if necessary.
So as my teammate said, there's two portions to our algorithm. There's an image processing portion and lighting control portion. This first picture shows the results of the image processing portion, and these pictures are not actually output to the system. This is just to help the camera identify better our target brightness values. And so what we start with a colored image that has a bunch of noise on it. We run it through a Gaussian blur to reduce the noise, and we also convert it to grayscale in order to read the brightness values. Then after that, we run it through a canny algorithm to enhance the edges, to show over and underexposed areas, and to also better help the camera identify our target brightness values. And this is the portion of the lighting control. Once it's run through the image processing portion, then we are able to send signals to our lighting controller, and from that, you can see in the first image, it's a dark image. We send to our lighting control portion, hey, this image is too dark, we need some more light, and our lighting control activates our LEDs, which then we get an enhanced and more well-lit image, as you can see in the second picture.
So what are specifications? Well, depending on our subsystems. So for our floodlights, obviously the amount of light was very important. Beam angle, had to make sure it encompasses a wide range to capture everything in a wide range. Power consumption, and for the camera, mounting assembly, thermal management, and image processing each have their own specific parameters. So resolution, frames per second were very important. Up to 60, but 30 is ideal. Field of view again for the camera angle. And then the mounting assembly material is obviously important for thermal management and radiation and longevity of the material itself. So we chose 6061 T6 aluminum. Give it certain parameters, constraints. So we went with 0.76 meters in height by 0.5 to 1 meters in base approximately. Math wasn't too critical, so we went with under 4 kilograms. Thermal management, we're still on the works with that with the heat sink, but we're looking at how much heat dissipate obviously, where to mount it, and the material we're looking at anodized aluminum, and of course image processing is suitable to the image quality itself.
So in order to figure out the optimal height and optimal distance of our lights, we had to do some calculations, basically the lights we chose came at a 150-degree beam angle. Using that and then using some trigonometry, we figured out what the optimal height should be for the mount, which came out to be around 0.76 meters and 0.2 meters for from the camera to the lights in the horizontal direction.
Alright, so this is the model that we made on SolidWorks. As you can see, it's composed of essentially 5 different parts. You got one that attaches to the base, 3 mid-shaft points, as well as the top. With our mounts, as previously stated, we did use a 6061 T6 aluminum. Reason why is it's good with tensile strength and it's also great with low density. We decided to have it as a cylindrical because we wanted to prevent any sharp edges for the astronauts. And we also decided to have it enclosed for dust mitigation as well as radiation. And inside is going to be the MLI insulator to prevent even more radiation from affecting our electrical components. As for the design itself, it's essentially a rotational mounting bracket. It's to have easy access with attaching and detaching. As you can see in the picture, it's 2 pegs on top and there's 2 holes on the bottom. The best way to visualize how this would work is if you imagine a smoke detector in your house. You just twist and pull off. And we'll show you right now.
Twist. Pull.
So in conclusion, we did use image data to control the lighting, and for our future work, we'll use a heat sink and then a power bank to aid in thermal management. And we will also make the casing larger so that the lighting and the camera will also move on its own.
Thank you for your time.
You created a edge detection algorithm, but is there any demonstrable evidence that this is superior to just simply using the brightness values from the image to determine if the heat is bright in the image or not?
Yes. Well, looking at from before adding the edge detection, we noticed that we ran into false edges caused by not having a clear enough picture. The camera couldn't really detect features as well before we added the edge detection, and then after we were able to see sharp areas of contrast in over and underexposed areas better, and we got better and more accurate values of brightness readings.
No, I'm asking if you compared your model using edge detection to your model without using edge detection as control.
Yes. Before the edge detection, we ran into issues such as having false edges and not completely getting the full picture, and it's not as accurate as it was after implementing the edge detection. So that's basically the purpose of the edge detection, just to help the camera really see features. For example, if we have an edge like this, if it's closer to the light, obviously it's going to be more overexposed, and anything on the side that's further back is going to be underexposed, so it helps the camera really know where the sharp edges are.
I have a follow-up question about the edge detection. So you're using the Canny algorithm. If I'm not mistaken, what you had said was that it's used to help find regions of over and under exposure. And then in the example you showed, it was kind of what you were just describing. You're talking more, to me, what sounded like object detection. So I was curious how it also applies to like exposure or like contrast detection.
From our research, when seeing over and underexposed areas, if we go back to the lighthouse. Like in this lighthouse picture example, what we saw was when we see edges, and then you see like in the middle, how you can't really see the lines we would consider that as an overexposed area. So we say that, okay, we don't need as much light on that as, for example, the house in the background where it's underexposed, we're seeing a lot more edges, and so we need to brighten that up more and not keep the part in front of the lighthouse as bright.
Okay, awesome. Thank you.
Thank you, team. right, good afternoon. Welcome back. Kicking off our afternoon session is University of Houston Clear Lake and Team Gamma Rays.
Hello, we are Team Gamma Rays. I am Allison Milanovich. I am joined by my teammates John Almiller III, Avery Barrera, Frank Blanchard, Brian Leon Estrada, and Grant Taylor. Today we are going to be discussing the development of our lunar scavenging and recycling unit, a concept we have been calling the Moonboat. So to give a brief overview of all the topics we will be going over, we have all these topics up here, and I'm going to be starting with the project introduction. So our project is basically surrounded over developing a unit meant for scavenging and recycling purposes on the lunar surface. However, Houston, we have a problem because currently there are no current methods for identification or recovery of these units, as well as no standards for recyclability or reusability. Additionally, our design has to be feasible, resourceful, as well as having an overall modular approach. Additionally, we have to have tools, robotic attachments, as well as methods for processing and repurposing materials. In addition to all this, we also have to adhere to the Texas Space Grant Consortium general requirements. So I'm going to be passing it off to Brian to talk about our constraints and criteria.
Thank you, Allison. Following our problem statement, we identified 6 key factors of our criteria. One of them will be energy efficiency. The other one will be durability, where our rover had to conduct multiple missions without failure as well. It has to be off-road, payload handling, system stability, and adaptability. Following that, we also have our constraints. One of them will be our budget. We were given a budget of 1,200 as well a time frame of 2 semesters, and our scale factor. We need to find a scale factor that can make sure that our components are not limited, as well our autonomous. We need to keep an autonomous system that will determine which parts will be semi-autonomous or full autonomous, and it's our power energy and our testing environment. Now I will be passing it on to Brent.
Thank you, Brian. This is also you. Okay. What happened? Am I going the wrong way? Oops, embarrassing. So here's all the man-made materials that's on the moon as of June 2025. As you can tell, majority of the objects are around the equator. There's around 500,000 pounds on the material as of now. The U.S. accounts for about 56% of that. And out of that 250,000 pounds, the Apollo missions account for 220,000 of that. We chose the Apollo missions because they are really, NASA has great records on it. There's modern LRO images, and they have a diverse stockpile. And from the Apollo missions, we're selecting the J missions. The J missions were the heaviest payload sent up there by NASA. And from the J missions, we are targeting the rovers from each one. There's 3 rovers. They are 80% metal, and we're going after the metal. Now I'm going to pass it on to Avery to go over the math.
Thank you, Brian. All right, so now that we have the J missions to focus on, we have 3 Apollo rovers here, Apollo 15, 16, 17. So how can we acquire the best power-efficient paths for our rover to actually get and acquire these payloads? Well, we did triangulation, which we leveraged Hypersine's equation to get the best optimal distance between the rovers. Once we were able to obtain that, we then got an average to actually find our center point. And as you can see here from the PowerPoint, the distances can go from as low as 460 kilometers to as high as 661. And this is just going through one pass from the center point to one mission. All right, so now for our scaling and testing. How can we best assure that we're using the correct physics, preserving them, while also being able to test here on Earth? That's where we leverage now the pi theorem. The pi theorem allows us to actually scale down efficiently while ensuring our geometry and being able to mimic the lunar environment and the soil behavior here on Earth. So with that being said, I'll now pass it on to John, who will go ahead and talk about the design.
Thank you, Avery. As you'll see, let me direct your attention to the projector, and you'll see that we have a full scale of our prototype. I'd like to direct your attention to the payload deck.
This is what we're going to try to use to secure our payload. It's going to be operated by 2 screw jacks, and it's going to be connected to our rover with pillow block bearings. It'll have a folding support system as well. The idea here is that we would lower the payload deck, make about a 20-degree angle with the lunar surface, and then we would then winch the payload onto our deck. Once we have that secured, we'd winch up and then lower our support system. Now, you're talking about pretty heavy here, about 500 pounds for the payload, about 1,000 pounds for our rover. That's why you're going to see our track system. Our track system is to make sure that we can, 1, tow our payload and have enough surface area so that way we don't sink into the regolith, and that we can conquer anything that we might see on the surface with the rough terrain. That being said, I'm going to pass it on to Frank to go over our future works and conclude this presentation.
Thank you, John. So for our future work, it's going to consist of creating a full CAD functioning model of the previous prototype design you saw in the previous slide. We're going to do a rough simulation on it using FBA software, specifically SOLIDWORKS. We're also going to implement a hazard detection and avoidance system and terrain and radar pathfinding. Yeah, I have to remember, we're a team of mechanical engineers. That's not going to really be our forte, but it is something we're going to implement. We're also going to develop a functional prototype model, and we're actually going to manufacture and assemble a scaled down model of this by the end of next semester, since this is a 2-semester project, and we hope to get present at TSGC. Ladies and gentlemen, boys and girls, and friends beyond the binary, we have a functioning lunar recycling mission rover that's ready to retrieve all of the Apollo J mission rovers. And our planned approach is to do this semi-autonomously and autonomously. And our current prototype model is still under work. And that's all, folks. Any questions? Thank you for your time. Yes.
So with Google's tracked design for this vehicle, it's very ambitious. I love it. But one thing that I'd like to ask: do you have anything, or have you put into consideration any kind of, again, any dust mitigation for those tracks? Because that's a lot of moving parts that are grinding up against each other.
That's a very great question, thank you. So we haven't done quite the dust mitigation research quite just yet. This is something still in the works. We just figured it'd be an optimal path of direction for our design due to the fact they're going to carry heavy payloads as the rovers from the Apollo mission, they are quite heavy. They're approximately about 500 pounds. So the track system itself is going to be quite heavy itself. So it's something we're going to consider in the future. We also are still looking at the possibility of having wheels. So we're just still open. We're not closed off to changing our design. It's still a prototype. It's just kind of reflecting where we're at this moment. But we'll definitely readjust as seen properly. Anyone else?
All right, thank you, team. Okay, and next up, we're going to have from Texas State, the Rad Dogs.
Good afternoon, everyone. We are the Radiation Tolerant Crew Laptop Team. We are radiation durable architecture withstanding gamma, or the Rat Dogs. We have JSOC, Sam, Stuart, and myself, the project manager, Hunter.
All right, so NASA is seeking to develop a radiation-tolerant crew laptop. They're working with Microchip to develop a radiation-tolerant processor, and we have chosen to go with an open-source computer architecture called the Framework 16. The problem that we're trying to solve is making a laptop that uses both of these components, but the processor that Microchip is developing only communicates data through PCIe. And unfortunately, the open source computer architecture, the Framework 16, only uses USB. So we're trying to bridge the gap between these two components to make a radiation-tolerant laptop. So why does NASA need a radiation-tolerant laptop? Our advisor, Justin Batista, he's working on the 2028 Lunar Gateway mission. So they're trying to put laptops on the Lunar Gateway. Obviously, they have laptops now on the space station, but that is in low Earth orbit. We're moving beyond that, so we need more radiation-tolerant systems. So this is going to be the overall block diagram showing you how we're going, or the system that we built to go from PCIe communication, connecting the processor to our controller, and then outputting the USB capability that we need to connect to the Framework 16. Ooh. We had to divvy up the work in 4 sections: the person in control, using the processor, the controller that does the communication between PCIe and USB. Second person, Sam, doing USB communications, making sure that it works. JSOC doing the PCIe communications, making sure that it works with the USB and is working with the processor. And then me doing the power integration between all the devices.
So like you said, I do the processor integration, which really is just a processor being the middleman between that PCIe and that USB connections. It's just the main host controller inside this processor is going to be the extensible host controller interface host controller. So this host controller, basically all it does is increase data flow. It's going to use 4 lanes of the PCI to reduce bottlenecking, and that's going to help control the balance and speed of our HIDs or human interface devices, like you saw back there in their demo, like a camera or a mouse. It's going to also support faster speeds like the USB-C that Sam's going to go more into.
So the USB subsection is incredibly important for adhering to the Framework 16 architecture that we mentioned. So I want to point you again to our block diagram, and I want to point out the USB ports at the bottom here. We have 2 USB-C and 2 USB-A ports. These USB-C ports are going to be super speed plus USB speed, and then the USB-A are going to be high speed. A quick qualification for the USB-C ports that we're going to have on our product: they are going to be non-reversible. That's actually a really important design choice that better supports the longevity of our project. And so what I want to point you to right now is the high-level block diagram produced by the other laptop team from our school, the Radcats. Y'all will hear from them shortly. You'll see in the orange section, the orange circle, excuse me, our chip, the PCI 11400. It is between the processor on the motherboard and all downstream USB hubs, and those hubs are the only places where we'll find actual USB ports on the laptop. So our host controller itself is not going to support any USB ports C or A in general. Now let's talk for a second about USB-C, because I did mention that they're going to be non-reversible on our board. And you're like, why? That defeats the purpose of the amazing USB-C. So let's look at the pinout really quickly. You'll see it's 2 identical sets of pins with one qualification: they are mirrored. And that is for that reversibility, so that if you turn the port over, everything's going to line up correctly. But at any given point, you're only using 1 set of pins. So communication is only going on 1 set of 12 pins. There's 24 total. So what that means is that we can shave off half of those, because in the final design, we're not going to need the full pin architecture to support any USB ports, because like I said, those are all from the downstream ports in general. Now, this will require some specific configuration from via the EEPROM, but Brian's going to go ahead and talk about that after he talks about the PCIe.
All right, hi everybody. I'm going to talk a little bit about the technology that we're using to package the information that comes from USB and goes out to PCIe and vice versa. So I use a pretty clever layering system. We're focused mostly on the hardware. It has a physical layer, which is the bottommost layer, it's just a pair of bidirectional wires that transfer information to the data link layer. The data link layer focuses mostly on maintaining data integrity, so it does a lot of double checks because in the environment of space, there's the threat of radiation could corrupt signals. So this is kind of like the protective shield against some of the radiation issues. That data link layer connects to the transaction layer, which packages the USB signals in a way that can be read by whatever you're connecting to. So that would connect to the software layer. The EEPROM holds the configuration memory for the device. So every time you turn the device on, it's going to check the EEPROM and just basically see how it should be functioning, how it should be set up. It stands for electronically erasable, programmable, read-only memory. And so that's really critical for configuring the board.
So I was in control of delivering power to the processor that does the PCIe to USB communications, also in control of PCI or USB, the implementer for them. They have standards on the voltage and current that needs to be supplied to each port. So without that, nothing works. This is pretty much the block diagram showing the power electronics design that I did. If you really want the nitty-gritty details of the MATLAB analysis to ensure the system stability or the Excel spreadsheet for all the calculations, I'd be more than happy to show you. But pretty much there's a main power supply supplying 5 volts, and the current that I calculated was 2 amps. Everything else was either 3.3 volts, 1 volt, or it was specifically a 5 volt V-bus for the USBs.
So what have we done this semester? We've done 3 main things in particular. First off, we verified the functionality of the chip that we're going to use, the PCI 11400, using an evaluation board provided by Microchip. We also adapted the schematics from that board to something that's more specialized that will fit into the Framework 16 architecture. And then we also conducted a trade study, and this weighed the value of going with that non-reversible USB-C option, as well as a few other options. And then Hunter's going to go ahead and describe what we're going to do next semester.
So like I said, yeah, path forward next semester, we finished those schematics, and so now we need those components to be laid out and actually connected on a printed circuit board. Once we get all that done, we're going to send that printed circuit board over because they're not through holes, so we cannot solder it ourselves. They are going to be surface mounts, so they need to be baked on. Hopefully we get that back during that design time so we can test it. Thank you so much for everything and everybody, Mr. Batista and Mr. Stevens for all your mentorship and guidance, Radcat Sentinels for all your mentorship and guidance and insight. If you have any questions, let's do it. Thank you. Let's do this one and then the back. I'm sorry.
Will you be modifying the framework in order to ensure that the ports are correctly used, that it can't be like misconfigured?
So the goal, as far as we can, is to not modify the framework design at all, because the modularity of the framework is the exact reason why we want to use that structure in the first place. So as soon as we mess with that structure, we start to lose some of the modularity. So even some of the design decisions that we've made have been so that we explicitly don't have to modify the framework. That's a great question. Thank you.
Yeah. My guess, this might be a ridiculous question, but you didn't take into account like the cost of it, but like the cost of like building the entire laptop.
Oh, okay. So no, we have not in particular, but we did talk. So like I said, so for sending that board to get the layout onto the board to actually have that PCB made is actually going to cost a lot of money. So next semester is actually something I will be doing as the project manager, is reaching out and trying to figure out exactly how much it is going to be and trying to get bids so we can just choose the lowest cost. And go ahead.
And you had also mentioned the cost for the whole laptop. Our specific project is a subsection of that. So the laptop design as an overall project is a multi-team, like multi-semester project. So that's kind of outside the scope of what we're doing here. We're working on one specific subsection. And then I think we're going to follow up. Oh, great.
And you're aiming to have this laptop be only good for like people like working on doing research in NASA?
For sure, exactly. On the space station, the gateway. So I guess one of the reasons why NASA kind of chose the Framework 16 is because, one, the open source, right? So everybody can kind of mess with it, but that also is going to save them money, right? So if everybody can play with it, they don't necessarily have to put a team in that designs all of that. So that's really where they're saving the money, but I do kind of understand where you're getting at. This is going to be a really expensive laptop, probably more expensive than any of us will ever buy, but for NASA getting it into space, I'm sure they're going to do what they need to keep the cost down, but it is going to be expensive. Thank you.
Thanks, team.
Don't get your laptop.
Don't worry. Okay, and next up, UT Tyler with Team Astroverse.
So, good afternoon, everybody. So, we are Team Astroverse, and we're in charge of designing / developing a rover for the Psyche 16 asteroid. We are a 2-semester group, and our department kind of has a little twist on this. So, we are designed specifically for the Psyche 16 asteroid, but we're also making this a very modular, lightweight system, so we can easily implement it to be used for Earth applications. So, my name is Juan Hernandez. I'm the team leader for Astroverse. Carter Haynes, Jar Vanessa, and Armand Domingo. Unfortunately, Kareem could not attend today. Let's jump right into some background. So, all this information I'm about to present to you about the Psyche 16 asteroid is hypothesized, and this is because the satellite is still not there. It's supposed to be arriving there early next year, and our project parameters are based on the hypothesized aspects of it so far. So, this asteroid is supposedly 30 to 60% iron and nickel by volume, which also has a really rough terrain surface, low gravity because it's in the asteroid belt, and has no atmosphere that's going to give us a lot of UV exposure. And its orbit is very funky, it's very elliptical, so its temperature fluctuations range from negative 60 Kelvin all the way up to 200 something Kelvin, so it's high range of temperature, and that kind of you're going to see later on when we go in depth with our rover why we choose a certain aluminum to use, and that's basically our goal, is to make sure it can survive this environment.
Here, what you see here is the rover that we are designing, and there is the open top view of the rover that we are designing, and we have a 4 DC motor that will be in charge to drive our motor, and in front we will have a 2-step motor for the direction, and we also plan to have aluminum shell since we are going in space and deal with the big range of temperature. Also, we will have the LS mesh grills. Next. Okay. We plan to have a modular chassis because, as you said before, we want to build two. We are working on two: the rover, the space one, and the Earth application. And the only thing that will move, that will change, will be the wheels and the shell.
So we have the wall structure of our shell. We plan on having these shells to be made with additive manufacturing, which allows us to have very strange geometry on the inside of the components. This wall structure that we have here is a gyroid infill that is pretty standard on most 3D printers or 3D printing slicing software, so if you want to ever check out the properties of it. It has good strength and rigidity in all directions. And the reason why we want to have this is because we can reduce the weight of the shell while still maintaining its rigidity and structure. Another thing you can do with this is you can also fill the empty space with a insulation or any radiation shielding that you want to just maintain space efficiency. So here's some of our FEA simulations on the combined shell and the chassis for our Earth application. So for our Earth application, we plan on having the shell be 3D printed in PLA, so it's a little weaker than the aluminum, but it's a lot cheaper. And so for the first one on the left is our dead load of 100 kilograms in the main payload section of our rover. And with that load, it only moves 0.06 millimeters, so not a whole lot. And then on the right, we have our torsional simulation. Because whenever it's moving around, you can easily encounter a situation where the terrain is applying a torsional load to it. And when we first did it, it seemed like 100 Newton meter torsional load, which didn't move it at all, but I stepped it up to 1,000 Newton meters just to see how much it would change or anything, but it still was only, 0.3 nanometers of deformation.
So for suspension, we decided to go with a rocker bogie suspension similar to what Mars is using right now. Our suspension goes with 3 parts, mostly the main arm, which is connected to the chassis, the rocker arm, which is we made it by doing a topology optimization, and then we will CNC it with a 6mm plate to have a precise model. And then we also are including a spring return mechanism for a stable system, and so that the rocker doesn't just go all over the place, but should return to its original position. We also simulated this suspension with a load of 100 kilograms. We are using the material as aluminum 6061 with a maximum displacement of 2.3 millimeters, which is fairly small compared to the amount of load we're implying, and especially since the suspension is also going to be included with the chassis altogether.
So you have a detailed look at one of our wheels for the space application. We're going with a nitinol airless mesh wheel. This is to make the wheel as lightweight as possible, but still have high traction and good durability, given nitinol's interesting properties. It should be able to easily deform to the terrain and maintain good traction.
This is the Earth application of our rover, the one that we're going to be building next semester. The only difference here is the shape, because here we have the payload section that you can see in blue, and the other difference will be the width, because we have the modular chassis. We're just going to use the same chassis and change the shape and the width.
Here's an exploded view for our Earth rover. You can see just different types of individual components, just like the chassis, the shell, the arms, the wheels, how they can all be implemented and changed over time depending on what type of mission we're going for, either space or Earth application, and how it is modular, such as the shell can be connected and switched out towards the chassis, and same with the wheels.
This might be hard to see, but this is like kind of a quick overview of our budget in order to build one. With all our aluminum, the electric components, mainly just being the motors, just to get it to move. And it's going to be right over $700. And when it comes to the space application version, we're going to require more aluminum just for that shell specifically. And because this is going to be a surface exploring rover, we're going to need some sort of sensors and scanners just to get an idea of the surface there. That should be still pretty much right under around $1,000 to build. And to close this out, so this semester we were mainly focused with designing it, developing it, analyzing it, and pricing it out, so that next semester we can start constructing it and testing it. And some ways we can test it is either with the provided NASA test bed, which is basically similar to one of the other routes, how they have a box with different type of surfaces on it. Or another way we can do it is I work for civil engineers, and we just take it to a construction site, throw it around on different surfaces and inclines out there. Thank you, and we will now be taking some questions.
The guy in the back said that raising it first.
I'm not sure if you said this earlier, what scale are you
Or like how big it is in general?
Yeah.
The chassis itself is 40 centimeters by 80 centimeters, so it's relatively small. And by our estimation, it's about 25 kilograms in mass. You think of a small rotor.
How exactly is it?
Sorry, what?
Sorry, what?
How exactly is this supposed to?
So for the prototype version, we'll probably use an RC car controller and implement that a certain way with programming. For the one that NASA will end up launching, that will be fully autonomous. So that one's going to be based with LiDAR sensors, which you can embed into the shells, and with LiDAR sensors and cameras and scanners.
So you mentioned the potential for including radiation shielding in the gyroid inflow of the walls of the rover. Do you have any plans of implementing that, or is this just a possibility that you're throwing as, you know, this is something we could include or could do additional work towards after we have completed this project as a whole?
It's more of an after thing because we're mainly focused on the Earth application rover, but it's something that's like, hey, we have this idea, we could throw the insulation in there or radiation shielding just to save on space and stuff. Guy on my left. Yes.
For your deformation analysis, how did you decide on the location and the size of the load that you applied?
So our department has a load in mind for that they want us to basically benchmark, and that way they gave us an estimated weight of about 100 kilograms, and then a lot of our other loads was based on the max mass of our rover, given our specifications that we came up with.
That, and for the space application version, on Psyche, it's more of a return and study their mission. It's not a return and come back mission. So we really focus on payload wasn't really there, just mainly on focus of making sure it can hold the components we need to analyze the surface there.
Yes.
How do you prevent the rover from flipping over? Because the gravitational field is only 0.15 meters per second squared. Any small bump could easily just flip the entire thing over.
Yeah, that part's pretty tricky, but for what we plan on doing is just have the rover just move very slowly. Also do a combination of not wanting to roll over our vehicle given the low gravity, but also power strengths.
All right, thank you, team. All right, and next up, San Jacinto College with the San Jacinto Flight Crew.
Hello. Hello. Thank you for still sticking around to see our presentation. We are, as stated, San Jacinto Flight Crew. My name is Gat Tran. I am the co-leader. This is my other co-leader, Jillian Landa. Team member, Jackie Velazquez, and other team member, Samantha Trino. So we are participating in the TSGC challenge as well as the NASA Suits challenge. So as some people here are first 1 semester, some are 2 semester, we might not know we're 2 semester or not, depending on our proposal is selected or not, and we'll go on detail for that later. We are developing your UI concept that is supposed to integrate with a rover, and it's called NOVA, which stands for Navigation and Operational Visual System. And so, to go over overview, I will hand it to my colleague, Samantha Trevino.
Thank you. As Dad has mentioned, we are working on the NASA SUITS project, which is designed to create new technologies to assist astronauts in the next lunar mission. So our solution is NOVA. It is an augmented reality that will be embedded into those helmets for the spacesuits to assist astronauts in a few key functions listed on the screen: navigation, measurements, collecting data and images, and keeping status of these suits. Our AR uses AI to recognize hand gestures in order to receive commands. A lot of y'all asked yesterday, how are we going to do this with the space gloves? We will train our AI with similar space gloves so that it works properly when they're out in space. Additionally, we would like to mention that our design that you will see later on is pretty simplistic, and this is done on purpose so that we do not obstruct the view of the astronauts. Let's go into the first key function, which is navigation. So a lot of us know about Where I Park My Car by Google and Apple. Our AI has a similar function where we can drop a pin and it will keep track of that location so that we never get lost. So once I land, I can mark this location as my landing site and I can travel left, right. I can go miles, I can explore further than ever before into craters and rock structures. And if I ever get lost, with a new hand gesture, I can get guided back to my desired points of interest. Now I will hand it over to our colleague, Jackie.
Hello. So NOVA also has a feature which is measurements. Measurements is very important whenever it comes to lunar missions. And so it just measures objects such as rocks and craters, right? And due to the time limit, obviously with the UI, you're not gonna automatically manually input the units. So that's why we input AI into the measurements, and it will automatically, the object in front of it will just automatically input that measurement. You know what I mean? But also it can give us clear measurements and yeah, the units below. Data is also very important if you want to do more in the futuristic. And so with data, it analyzes images and it takes images and measurements pretty much. And so it keeps us organized and keeps us in track. So image viewing, we're able to zoom in, zoom out, and take pictures, obviously, so we can look back into it. And it also, whenever you take a picture, it marks the coordinates of where you took it and what time you took it. Data organization, so let's say we take a picture or we measure something, it's gonna go in the individual folder that it's given over here, rocks, craters, terrain, features, and objects. Also, we do data tracking, so measurements is such an important thing. So whenever you measure something, it's gonna detect what time you took it and the coordinates of where you took it, so we're able to go back into it. So now I'm gonna pass it to.
Hi everyone, I'm going to talk about the last feature we have. So the last feature we have is status. So as my colleague mentioned earlier about the SUITS challenge, what happens is they end up taking all the teams and they split us into two. Half of us will do the spacesuit interface as we're presenting to you today, which was our proposal, and half of us will be doing the rover. So what we decided is, as a UI, we have to have functions that also are compatible with the rover, as well as with the spacesuit. So for the rover, as we will be collaborating in the spring, we'll be able to collaborate and ask, hey, what functions do you think are important? What do you think we should add? What's important? So right now we have rover temperature, rover signal strength, rover battery. As well for the spacesuit, we have oxygen, suit pressure, and signal strength. So we also made a conceptual UI for a demonstration. And I'll give a little background. So obviously, we're concept right now. So what I have here is you follow with the mouse, but essentially you would be using your hand. So as you can see, it's heading to the right, click in the menu. Then it opens up with 4 options on the left. You have camera, navigation, data, and status. You have the camera, there's your camera. You would end up using your signal, your 3 seconds to take the picture. You had back, navigation. Give your arrow how far you are, where you're routed to. You head back, then you open up data. As talked about earlier, we have measurement, navigation, your images you saved earlier. And student status we were talking about earlier. Okay, so we also want to talk about our community outreach. So we did community outreach about 2 weeks ago. We went to the San Jacinto College STEM Expedition where we were able to meet with students from elementary all the way to high school. Because part of this is kind of interaction of what do people, we want feedback, right? Because we're going to do this in the spring, so we want anything that you think we can benefit from. So we were able to talk to students, get them engaged, and kind of introduce AR, VR as well. A lot of people are familiar with VR, a lot of people are familiar with AR. So, and yesterday, as you saw with our poster, if you came around, we did have a QR code that you can scan and give us feedback on, which we will be having at the end of this presentation, so we would really appreciate if you were to scan it and give us some feedback. Thank you.
And since, let me roll back to the NASA students. If our proposal is selected, then we can move forward and actually have something functional and built. Because currently everything is just purely conceptual. So there's no results, data, like prototyping or feedback we have right now. So ideally we would want to have something like that built in the second semester. On top of that, this is supposed to integrate with a rover. So it would be ideal if we could collab with another group that's in development of a rover that's modular, it's got different cell functions, lights, camera, hazards awareness, situational awareness, good wheel design, power delivery, good signal strength, all that. And something that's modular, it's great because if we're developing more functions, because right now it's not limited to these functions, it can be more depending on what astronauts need. So if something's modular, we can add more function to it. And that's gonna be great. Also, it can also be good for like Earth applications. So with that, I will hand off to Samantha for conclusion.
Overall, Nova would assist us in navigating and exploring further than ever before. What makes Nova so unique is that we are able to implement back the human experience into exploring the moon. When it comes to gathering data over the past few years, we tend to lose a little bit of the emotions that tend to impact people. So adding back that human experience would really speak to the masses and influence future generations to exploring space again. We would like to thank our faculty, Dr. Rashid and Dr. Bishwa. And we would also like to thank our NASA mentor, Neil McHenry, for their assistance. As you can see on the screen, we have the orange QR code for you to provide feedback, and we will open up the floor for questions.
Yes.
Why did you avoid using pictograms or any kind of visual language in your UI? You seem to use a text-only kind of based system.
Well, we're not really focused on the visuals right now. We're just fully focused on whether enough the functions can actually work. In the beginning, we're doing everything in Unity, and we're just we're struggling trying to get the buttons to interact. Once you select this, it opens this, and so like visuals like what we have right now, it's just there, so you have a good like idea from what their point of view is.
One thing I'm slightly confused about is how you're going to use AI for the data entry in terms of like the what's called in terms of the unit size lead you guys are going over. Is it going to be something like voice recognition software so that you can just like say this is 50 feet that way, and this was 42 centimeters that way.
So the idea using AI to do machine learning, say like if we pick up like a sample of rock, the idea is to have the AI or the UI to recognize an object and highlight it. Okay, it recognizes it as a rock. But initially, you'll have to be taught that. So it'll be like a process of prototyping. We don't have that right now, unfortunately. It's purely concept. So if we get to move forward, we'd love to do some sort of like feedback and build upon it. Thank you. Any more? Yes.
So are you using like a model that already exists, or are you completely making something just specifically for?
Oh, can you speak a little bit louder? Sorry.
What I meant to say was, like, trying to follow up with the AI. Are you gonna make a model out of scratch, or
Yes.
do you want to use like a model?
So everything we've made in terms of like functions and UI and aesthetics and order and customization, all that's been built up from scratch. We took some inspiration from like movies, video games, stuff like that. Whatever is like aesthetically and user friendly, something that's simple. We just went with it. Any more questions?
All right, thank you, Keith.
Thank you.
All right, that ends our first afternoon session. We'll take a quick break and come back at 2:25. Okay, if everyone could have a seat again. Kicking off the last session of this afternoon, we have the University of Houston Clear Lake and Team Interstellar Innovators.
Thank you. Good afternoon, everybody. We are Team Interstellar Innovators. We are doing our first semester of 2 on the Microgene Next B Passive Capture Tool Dock competition in tandem with the TSGC. My name is Cal Harper. We have Magali Chavarria, Vivian Liu, Garrett Stevens, and Juliet Weber. For our presentation today, we're going to be talking about the introduction, our requirements and criteria, relevant codes and regulations, as well as our preliminary design concepts leading into our final design, touching on our finite element analysis, discussing our bill of materials, and then talking about our future plans. And I'm going to hand it off to Garrett to discuss our introduction.
Thank you, Cal. So just some background to our project. Extravehicular activities, or EVAs, are critical for maintenance on the ISS, where astronauts frequently find themselves in constrained body positions where their movements are restricted. These astronauts on these EVAs also stow their tools on something called an MWS, or a multi-workstation swing arm. The current securing mechanism requires a dedicated install actuation with switches and lock like the on-orbit use of the bayonet and tether. And our objective is just to design a EVA tool dock that allows one-handed tool installation without any dedicated install actuation. So some requirements, criteria, and constraints. So requirements, it needs to be single fault tolerant, needs to have a blind one-stall installation and retrieval, compatible with the NWS swing arms, EVA glove friendly, needs to be non-buoyant, which will be tested at the NBO if chosen, and it can't have any dedicated install actuation. And then some constraints that we have to follow during our design process is it needs to stay within a volume of 5 by 5 by 5 inches. It can't exceed a weight of 2 pounds. Max install force, 10 pound force, max install torque of 1.5 inch-pounds, and it needs to be able to support at least 15 pounds of weight. So we took those customer requirements and threw them into a HOQ, comparing them to engineering characteristics, just so we were able to check all the boxes when we went into our design process for this tool dock. And then we also followed relevant codes and regulations, mainly sharp edges and pinch points, removing those so we ensure crew safety and mission success when astronauts are on these EVAs. And I will hand it off to Julian to go over our preliminary design concepts. Thank you, Garrett. Now that we have our requirements, constraints, and house of quality established, we're ready to start generating design ideas. So here are our 4 preliminary design concepts we developed. Our concept 1 is a holster idea. It's inspired by a key style guide system. Our concept 2 is the buckle, which works similar to a backpack strap. Our concept 3 is the snap dock, inspired by snap fit closures. Concept 4 uses a coupler system, or a coupler mechanism similar to a Janey railroad coupler. And after laying out these options, we need a fair way to compare them. So that led us into the pew chart. Here we used a pew chart to evaluate each concept. This helped us compare them directly to the current system, the bayonet and tether systems. We scored the concepts based on our key requirements such as one-handed install, blind install, compact size, EVA glove compatibility, and more. From the results, concept 2, the buckle, performed the best overall. With that design chosen, we moved forward and developed it into our final design. I'll now be passing it to Vivian to talk about the final design.
Thank you, Julian. So our final design, as Julian stated, it iterates on concept 2, where we changed the geometry of the pin and the base of the buckle to increase the surface area for stress reduction based on some of our previous preliminary stress analysis that we did. And then we also addressed some sharp edge concerns where we rounded the buckle base and the buckle prongs as well as the buckle edges. The overall dimensions of this component, the side release buckle in total, It's going to be 3 by 3 by 1.5, which is under the constraint of 5 by 5 by 5, so we do meet that requirement. For our product architecture, the side release buckle, it does have 2 different types of components. One component is the belt component. It attaches to the MWS, and then the tool component attaches to the tool, which is the PGT, excuse me. And so some key features that we have the taper alignment slot, which it helps us satisfy that one-handed blind install. And then we also have the buckle, the pin, and the side, the curves flat springs. Those are going to help us with that single fault tolerance. So if the buckle fails, we still have that the pin as well as the curved flat springs. And then the side release buttons, we do have, that's going to be a release mechanism, which I will pass on to Magali to talk more about.
So on this slide, you'll be able to see an expanded view of our tool component. As just stated earlier, this is going to be attached to the PGT or depending on what tool you're using at the moment. This will feature a set of 2 buttons and a set of 2 springs. It'll have a built-in buckle housing where the buckle will be sliding in place, as you'll see in the next slide, and it'll also have a built-in pin. On the next slide, you'll see an expanded view of the belt component, having a pair of curved flat springs, having built-in spring supports for the curved flat springs, and as you mentioned earlier, that taper alignment slot providing that easy one-handed blended installation, as well as the built-in buckle. On this next slide, you'll be able to see the animation. Sorry, I might blind you a little bit. So you'll see the pin kind of sliding into place, causing enough displacement on those curved flat springs. And once it's past that, they'll fall back into place, locking it in, while simultaneously the buckle over here on the side will be coming into that built-in housing and locking into place. Now, in order for the astronaut to release that, they have to press both buttons in order for it to dislodge and pull up. But when pulling up, they have to pull up with enough force to cause that displacement once again to the curved flat springs to be able to fully release. And I'll go ahead and pass it off to Cal to go over our analysis.
Thank you, Magali. So for the finite element analysis, the initial look that we had for our finite element analysis is for the side release buckle to hold the pistol grip tool. So on the left side, we have the tool component. On the right side, we have the belt component and how they react to the stress of the 15 pounds of pistol grip tool. For the tool component, we see the maximum stress occurs within the buckle housing, but we still see some of the effect of the stress on the pin of the tool component. And for the belt component, we see that the maximum stress occurs within the screw clearance holes, but we're also still seeing some of that stress effect on the buckle as well. In addition, we also wanted to focus on the deflection that would occur on the prongs of the buckle. So using the maximum removal force on the prongs of the buckle, we get a deflection of 0.05 inches. And I'm going to pass it along to Julian to talk about our costs.
Thank you, Cal. So here's our estimated cost breakdown. This includes only raw materials since printing is going to be done at our UHCL 3D printing lab. Most of the cost comes from PLA for early prototypes and tough PLA for our final 3D print. We also included a small cost for music wire used in the spring mechanisms. Altogether, our estimated total cost is about $244. With those costs in mind, here's what we'll be doing next semester. Next semester, we move into full prototyping and testing. Our plan is broken into 2 major stages, prototyping and testing. We'll start by printing PLA versions to verify geometry and tolerances and adjust the design as needed. After that, we'll incorporate the springs and create our final tough PLA prototype. Once the final version is printed, we'll begin testing for life cycle, durability, repetition, fatigue, and EVA glove compatibility. By the end of the semester, our goal is to have fully functional tested prototype ready for evaluation. I will now pass it to Kyle to conclude us.
Our side release buckle will be able to reach these design requirements, focusing on our one-handed install, our blind installation, ease of use, and EVA glove compatibility. And the next slide, we have all the references. And if you have any questions, please feel free to ask. Yes.
So the release mechanism is like pinch the two sides to a situation.
Yes.
So like I could see like someone completing the pinching action with one hand, but then removing the tool would also take. I mean, not to say like.
Since the since the buttons themselves are on the tool component,
okay.
it will allow them to lift in one action.
Sorry.
In addition, the MWS, and I don't know if the picture that we had gave it all that much justice, but it kind of sticks away from the hip as like an extra arm almost that is rigid and kind of supports outside the astronaut's main body, so they can easily kind of reach that area. So our goal is to make sure that they can easily reach this in any position, and that they can do this without even having to visually confirm that it's on the part.
Thank you, team. Cat Sentinels.
Good afternoon, everyone. We are the RadCat Sentinels from Texas State University, and our project is the Radiation Tolerant Crew Laptop. NASA's looking for a powerful and energy-efficient computing solution for their upcoming lunar missions. As a result, they've collaborated with Microchip to create a 64-bit RISC-V radiation-tolerant processor called the PIC64 HPSC. Throughout the rest of my presentation, I'll be calling this the PIC64. Our job is to take the framework laptop and redesign the internal architecture to support the communication interfaces offered by the PIC64. What this means essentially is we took the framework laptop, we swapped out the processor with the PIC64, and then we figured out how this processor is going to communicate with all the internal devices of the framework laptop. Here we have the high-level architecture definition. It's a bit complex. All I want you guys to take away from it is that in the middle we have the brain of the computer, the processor. All the lines coming off of this are going to be the communication signals used to communicate to the devices. How exactly the processor communicates with our devices will be explained further in the presentation. The HID, or Human Interface Devices Subsystem, is responsible for managing all user input as well as providing some output for the user. The main device utilized here is going to be the PCIe 11400. This device is a PCI to USB bridge. What that does essentially is it takes PCI signals from the processor and it converts it to USB signals that can be used by internal devices. Thanks to some work done by our other team, the Rad Dogs, we're able to use a configuration that uses 2 downstream super speed plus USB lines and 2 downstream high speed USB lines. For the USB, or for the HID subsystem, we only use the high speed downstream lines. You can see here that they're routed to 2 separate USB hubs and then fanned out to all the human interface devices for our system. The USB system allows for external connections to be made with our system. The main device again utilized here is going to be the PCI 11400. Without this device, our entire system doesn't work. Again, here we're going to be only using the 3.2 Super Speed Plus USB lines. Those are going to be routed into 2 separate USB hubs and then fanned out to 6 external USB-C physical ports. Thanks to the modularity of the framework's design, we're able to use these expansion cards, which you just click into the external USB-C ports, and it allows for any kind of external connection you might want for a laptop, whether that be USB-A, B, C, micro SD, HDMI, or even Ethernet, which we'll get into in this next slide.
So the Ethernet is going to be used with one of the USB Ethernet expansion cards. So that allows us to keep the modularity of the framework laptop. The caveat to that is it's not going to be quite as speed efficient as maybe like a hardwire connection straight to the PIC64. But with what our use case is, it's going to be completely viable and it'll work. Our main use case is going to be using something called EtherCAT. The laptop will act as the EtherCAT master device. So you kind of think of that as like a coordinator that will send Ethernet packets to different EtherCAT slave devices, and the slave devices will then receive them as it's going along the stream. So the EtherCAT devices will need a more high-speed, time-critical performance out of the Ethernet, but the master device, which the laptop is, won't necessarily require the same constraints. Another thing that's super important to highlight with the USB Ethernet expansion card is that it does have a normal network interface controller to the operating system. And essentially what that means is the computer is still going to identify it as an Ethernet port, which is a requirement for the EtherCAT protocol. For the graphics subsystem, it's fairly straightforward. So we're using 8 PCIe Gen 3 lanes, and what that does, it allows us to leverage the already pre-existing graphics card that the framework comes with. The reason we want to do that is creating a graphics card is a huge task for redesign, which can take a lot of time and cost, which is what we are trying to minimize. So having the 8 PCIe lanes allows us to use a pre-existing card. This is then connected to an EEP panel or an embedded display port panel. You can think of that kind of as like your laptop screen, the top part of the laptop. And then that's going to be connected to a downstream 2.0 USB port. This is going to be for things like your microcontroller interface, your touchscreen input, your ambient lighting, and other auxiliary sensors. And then you'll also have another USB connection to the graphics card, which will be for things like BIOS or firmware updates. And this is all thanks to the Red Dogs. With the PCI 11400, we were able to configure the USBs in a way that freed up those PCI lanes. So we had 8, because for a while we only had 4 without the redesign.
The storage and memory subsystem is responsible for how data is temporarily or permanently handled. For the memory subsystem, the HPSC provides 2 DDR interfaces, DDR3 2133 MHz and DDR4 3200 MHz. We chose DDR4 3200 MHz because it offers significantly higher data transfer speeds. The HPSC also provides both 72-bit and 80-bit interfaces, which provide error correction capabilities. We chose the 80-bit configuration because it offers 2 bits per byte of ECC rather than the 1 bit per byte its 72-bit counterpart provides. We also chose SODIMM over soldergram in order to fit the framework laptop form factor and maintain its modularity. For the storage subsection, the HPSC framework laptop supports 2 M.2 2280 SSDs at PCIe Gen 3 speeds. The use of 2 SSDs allows us to use redundancy and partitioning strategies in order to increase reliability and fault tolerance.
The embedded controller, also known as the EC, is a low-powered microcontroller that manages the system's peripheral devices and the HID inputs from the input module. It operates independently of the HPSC processor and performs tasks such as power control, system monitoring, and real-time input processing. while designing our systems architecture and referencing the Framework 16, we noticed that their EC used ESPI. The problem with that, they used ESPI for their primary communication interface. The problem with that is that our RISC-V HPSC does not support ESPI. So what we needed to do is we had to find an embedded controller that used the standard interfaces that the HPSC would use. Luckily for us, Microchip, the same manufacturer that makes the HPSC, also makes the same L10, which has full I2C and SPI functionality, making it fully compatible with our RISC-V HPSC and allowing for future teams to develop firmware without having to worry about Intel's proprietary ESPI.
We'd like to thank our genius sponsor, Mr. Bautista, as well as our very handsome faculty advisor, Mr. Stevens, who grades us. We'd also like to thank all the beautiful judges who also grade us. And finally, Mom and Dad. Any questions? Okay, nice.
Presentation this afternoon from Texas A&M, the Aggie Knots.
Howdy. My name is Emily Nelson. This is Samantha Goebel. This is Samuel Corrigan, David Gonzalez, and Gavin Moore. And we are the Aggie Knots from Texas A&M University. So our problem is to try to find a physiological countermeasure for extended habitation and reduced gravity. We decided to do this using the VersaClimber. So our mission statement is to design and build a prototype of an exercise device that can maintain the cardiovascular health of astronauts while in deep space. This device needs to meet physiological, environmental, and payload constraints to ensure proper use and function. So what is orthostatic intolerance? This is a group of conditions where a person experiences symptoms like lightheadedness, faintness, fatigue, dizziness while standing up, but they feel better when lying down. So astronauts typically experience this upon return to Earth because while in microgravity environment, they have a cephalid fluid shift, which you can see here. So this astronaut, before space, he's normal. While he's in space, he experiences this fluid shift upwards, so he's got what they call puffy face syndrome, just meaning that he's got excess of fluid up in the head and upper body region. After flight, he's feeling dizzy or woozy, so they're carrying him. This is a common practice for astronauts upon return to Earth. So they can often experience this for months after this issue occurs.
Okay, so we looked at different case studies and statistics from astronauts and missions, and we found that this can happen to up to 30% of returning astronauts per year. And then from the statistics we saw, it's happened to about 109 out of 360 total astronauts that had reported this orthostatic intolerance. So the problem is, the heart of the issue is that astronauts are losing aerobic capacity while they're up in this reduced gravity environment. So the solution we're trying to find is something that can help them maintain this aerobic capacity, but something that also can integrate into current systems in the space stations and facilities that they currently have.
So why use a VersaClimber and not some other kind of device? So the idea was we were thinking about something that would draw inspiration from the Arid, you can see there at the bottom, and the Colbert, or the T2, which is the treadmill. We want something that's resistive, but also allows us to do something that improves your cardiovascular health. Think something like aerobic exercise, like running on a treadmill. So we nailed this down to either VersaClimbers, a Jacob's ladder, or some sort of elliptical. And you can see some of our drawings here. We also did a study to decide which one would be most efficient based on just calorie burn per speed. The one that won by a large margin was the VersaClimber, as you can see. From there, we did a Q matrix, and we compared it mainly to the Colbert, focused on the aerobic area here, and the VersaClimber one again. But what really cemented the final concept selection was the idea that the VersaClimber, like the Colbert, could have a harness system, in this case bolted behind you to be in tension and mimic a body weight load, which the other devices were either not able to do or not able to do as well. Lastly, it's modular, and you could add the resistive element of the pneumatic element right there that my friend Gavin has.
So in order to further validate our design, what we did is we did a motion biomechanics analysis. So using motion capture, we evaluated the joint angles in upper and lower extremities. What we observed is that using the VersaClimber, we saw similar or even more joint range of motion compared to running on a treadmill. We also use this data to study the accelerations. So this is more of a qualitative test, but if you look here on the left, we got the climbing, and on the right we have running. So just looking at these graphs, what you see is that it's much smoother for the VersaClimber and much spikier for running. What that translates to is less vibration on the VersaClimber, but also less load on joints, which reduces risk of user injury in the long term. We also have this resistance system here. So this is a dual-acting cylinder. It's designed to generate about 100 pounds of force, which is based on standards by NASA. And the reason why we chose this system out of, say, a motor or magnetic resistance or even elastic bands is that this one has the best fire resistance, so the lowest fire risk, and it also has very good wear. So that's why we strayed away from using elastic bands for our resistance system.
So for the actual design of the VersaClimber, to stress test it, we essentially put a force on top of the VersaClimber in SolidWorks, and with the aluminum alloy of 2024-T3, it showed it to resist loads up to 6.8 thousand newtons. And then reducing the weight of it, we have this strip design where we essentially took out large chunks of metal along the main beam and the same aluminum, and it reduced the weight to 8 kilograms, and that still had a force resistance up to 1.8 thousand newtons. And then the design that we're going to go with of the honeycomb still reduced the weight a fair bit and got us down to 8.5 kilograms while still showing it resists up to 4.5 thousand newtons. And then additionally, on the inside of the actual pulley system, we did the honeycomb design again to more parts to further reduce the weight, and that again showed high resistances of 12,000 newtons.
On top of those designs, we also want to look at fatigue testing. So currently VersaClimbers are rated for three years of use at 3 hours a day with regular maintenance. So we analyzed the design and identified failure modes. So 2 points of failure are those cables, as you can see in red, and those wheels in green. So our potential plans are swapping out the materials, so using something like Teflon or Delrin for the wheels, and then using some kind of a cable with a higher tensile strength.
So we also performed a vibrational stress study utilizing frequency analysis in SolidWorks. So the ideal vibrational output of our device needs to be between 1 and 1,000 hertz for it to output on the shuttle. And this is all of our outputs were well within this range we do not believe that there should be any problem with the vibrational output of our device on the space shuttle. Furthermore, space shuttle payload vibrations in the operating environment exerted are incredibly low and should have no negative effect on the VersaClimber.
Okay, a little summary of what was important from what we just talked about. So each piston should be able to provide about 40 to 60 pounds of force, resistance force, but we're also going to implement the harness system that will provide additional resistance. And then the range of motion exceeded what we had found for the running standards, and with the material and design changes, we were able to reduce the mass by about 70% in our simulations.
Proof of concepts, just to sum up, we got a harness system, we have a climbing system that is better than running, and we also are able to withstand the vibrations that we need to. Future work is just implementing this honeycomb structure, making a collapsible design, perhaps telescoping, and working in a user interface. We'd like to acknowledge our two faculty advisors, Dr. Jeff Reynolds, Professor Zachary Munach, and our NASA mentor, Colonel Fossum. Any questions?
The honeycomb patterning that you have for the aluminum, is that going to be a significant increase for like manufacturing costs, or is that like a type of aluminum that you would run into or be able to purchase readily?
So first of all, the reason why we went with the aluminum is that specific design, we can use a CNC water jet mill. So we can just use those facilities that we already have available to us. So that saves us having to remake it. We can just use what we already have and cut that out.
Ricardo.
Do you have any safety considerations for if the astronaut slips while still harnessed to the tension harness?
So yes, there will be some safety restraints to ensure that he can stay on. So he shouldn't slip at all due to the fact that there will be straps on his feet. So there is a current model of our pedals right here which has that, but we will also be implementing another design in which the foot would clip into the foot pedal. Furthermore, the hand holds are pretty good, and since the harness is also connected at the front to the device, it should be no issue. Yes, Preston.
So the effect of gravity pulling the body down is obviously going to help the climbing and the exercise on Earth. How are we going to kind of account for that in space?
I'm sorry, could you repeat that?
The effect of gravity as you're pulling up and using your muscles is a lot on Earth. In space where gravity is less, how are you planning to account for that?
So, in this very pleasant picture of myself. Well, to mimic the gravitational pull, we're going to try and keep it in tension. So here on Earth, you can be in tension if you hang from something, but in space we have the base. So we're trying to make a base as well. That's a good question. And an anchoring system that'll keep those taut, especially as you lean forward.
Have you guys done a cost-benefit analysis to see how worth it would be to attach some sort of generator to this? Because there's likely some sort of wattage to come out of a person doing all this work. So while it won't produce a lot of power, it certainly isn't nothing.
So that's a really great point. So we've considered it, but the reason why we don't want to pursue that right now is because using some kind of a motor involves some kind of a spinning or like a flywheel system. Those kinds of flywheel systems have a very high fire risk. That's also why we went with this pneumatic piston design, is because it's a lot harder to start a fire with a piston versus some kind of a motor. So we could pursue it, and it's something worth looking into. We would just have to find a way to mitigate that fire risk, especially with the high oxygen environment seen inside the cabins.
Next question. If possible, are you able to show us in recent demonstrations?
Yes.
Yeah.
Let's go!
Thank you, team. All right, that concludes our student presentations. Let's give every team another round of applause. So over the next hour or so, you're going to have a break. We'll have a poster session. We'll have some snacks outside. You can grab a cookie or brownie. We are going to be aggregating all the scores. So you've been scored on your video, on your poster, on your peer review, and finally on all these oral presentations. We're going to assemble all of those and have the award ceremony at 4:15 to recognize our top teams. We'll see you then.
My mom says that she's very proud of me. They're probably going to they might stay David
Brian and Sam are giving a talk right now. Connor.
Thank you for taking the bullet for the rest of us. I would have hopped on this. I have tools. Yeah, you too. You want us to do your remember that you have a tail. Yeah, that's why I like to carry it with the first. Just tell them to come talk to him over here. Yeah, probably.
Y'all want to kind of keep up over here?
Posters are in front of the projectors.
Yeah, y'all making it.
No, I'm not. No, yeah. I'm not. Is that everybody?
All good to get in here. No, I mean, having all the students is short as we said, and then you. Yeah, I'm getting Mr. C. Dump short. Yeah. shuffling. Last one and two then. Yeah. Just tell me to shuffle. Are you smiling? Are we? Nope. You get one and I'll grab the other end. That's great. It's the other camera scenes, right? Say Bobcat. Oh, it's one upside down. You know this is doing. Does everybody know the hand thing? What's the hand? Everybody know the hand thing. What's the hand thing? Yeah. On the right. Is that on the right? Oh, wait, am I wrong? We don't even know. We're just messing around. All right, Mr. Stevens. Oh, wait, we got to get Are we in here?
Yes, you are now.
Gotta make sure that your LinkedIn posts look good.
That's right. You're too kind. Oh my God, I never noticed those this. Oh my God, y'all are cool. Good joke. I don't think so. It's just a no, that's a Sabbath. They're judged. That's okay. It's a little touch and right? No, that would be fun. Oh, yeah? We get high. Yeah. I'm curious.
Maybe like there's I know like I was like if I was on the
Oh, like build a model of it?
Oh, we get two good. Yeah. I think it was just there was never a countdown. So there was like only two photos where everybody looked good. Like everyone was always half the photos are really like, oh my goodness. Yeah, right? Texas on the left. Right, because it's like, if you're looking at me, this looks like Texas. This is backwards. Am I tripping? Right, yeah. Yeah, right.
was that I didn't know if you were defining how you were defining that swap, and there is a certain amount of like also for like battery circuits, hot swap circuits are designed to be a direct switch over to operation and directly, maybe you'll work towards that, maybe you have it implemented, but for instance, like your microcontroller, because it runs everything, it's not, it can't necessarily be hot swap. But again, I love.
That's a good point. That's what
and that's why it's like a kind of a niche thing, and that's why, and I don't think that it was like an appropriate time to do the presentation. Because I thought it was just like, oh, sort of like maybe you were using it as a different way. I had used it before or something like that.
We probably have a more official version.
Yeah, and I didn't know, I really don't think it was like a gotcha. You know, I think any sort of feedback should be positive and abstract. It's a cool project. Quickly disconnected the insert, like something that was very easy.
So what would be a more appropriate?
I think like homogenized. I think saying all of them I think that's a little bit better way to put it. To me, a hot swap will just implies during operation.
Okay, yeah, that's good enough.
Yeah. No, I seriously, I really.
Oh, that's a sick project too.
Thank you. Yeah, absolutely. Where, you know, we're focused, like you saw in the presentation, we're focused on delivering fast, reliable illumination. And also, so, for instance, how is it, so, a little better, with our system, you know, we have to spend a lot of time focusing on the geometry, and that was always like, we have that are both high and low, so that we cover different sectors and make sense of like, modular and can be scale, can be expanded, etc. But this is going to be something that we're going to change. This is how we make decisions using a modern it contains color information. So it's sensors are tuned for red, green, blue, and they tell you, okay, this is how intense the red channel is, this is how intense the green channel is, and then it's displayed on top. The monochromatic is just tiny pixels. All it does is just basically how much radiance is coming off. And using that idea to identify, okay, instead of you say, if you're under, in this case you can see the threshold. So if you're under 25, we're calling that a dark pixel. If you're above 25, we're calling that a white pixel. And then the sector percentages are total number of dark pixels in the sector relative to the total number of area. So once we get there, we decide, okay, if we're under a certain darkness threshold, we need to shine lights. So then once we implement, you know, we get to that state and we decide we want to shine lights. We're using a PID scheme, but really key on it. We don't have any derivative again. We just have a integral. It's so helpful. The math tools were so helpful for figuring it out because once we characterized the system, we did this pseudo-random binary sequence. Flash the lights, hundreds of frames, and see, okay, we turn the lights on to 255, 200, etc. And then we build an idea of, oh, this is how much the sector percentages, the scene changes overall based on this light. So you build a model for your entire system. And then once you have that in place, you're able to use it in the map. You get an idea of how to control
Some values corresponding to the sector that correspond with how bright it is.
Yeah, I think this whole thing, you know, Actually, I'm sorry, it has a higher helping. So it's right, but it doesn't stack. Hold on, I'm mixing up the albedo. I'm sorry, I screwed this up. What we care about Lights are always going to be hungry. It's really crazy.
As you saw, they're meant to and we're just putting this thing on and all the time. It does not have any after this, we can work the same. Yeah, the idea was that something like this would be attached
Good lighting.
flash lenses. Power. It's kind of one of the times we had so many things that we never got to.
It makes the modularity a bit easier. Whereas since our system is just receiving rights from our computer systems, we can integrate into our stuff is
Okay, welcome back, online viewers, to the Design Challenge Showcase. This is our recognition and awards. First, I want to thank our guest speaker again, Tyler Gilliland from Intuitive Machines, all our showcase judges, NASA mentors, faculty advisors, and other supporters. Let's give them a round of applause. And then most of all, you students who persisted and came up with excellent designs. You're a credit to your institution. So round of applause for all the students. Okay, here we go on the awards. So we have 4 different categories: Best Video, Best Poster, Peer Review, and Oral Presentation. Combining those scores, we come up with our top design teams. And the first 4 places earn scholarships. So per student, 4th place will earn $500 a student, 3rd place $600, 2nd place $750, and the top design team, each student will get a $1,000 scholarship. All right, so first up, Best Video, as judged by our judges. In 4th place, you may see them. In 3rd place, Tarleton Rellis LTV. 2nd place, HCC Pioneer. And the top video from our judges, Texas State, Boss. Okay, next category, Best Poster. So these were judged with your posters you submitted. 4th place, Texas A&M 12th Grand Bioculture. In 3rd place, Texas A&M Aggie Nuts. Second place, Texas State Radcat Sentinel. And the top poster, Tarleton Rellis LTV. Okay, here's where all your efforts came into play. The best peer review. And I don't know how, after 23 different scores of all the other teams, somehow we came up with a tie for 3rd place. And it's actually a 3-way tie for 3rd place. So, 3rd place, best peer review, Texas State Radcat Sentinels, UH Clear Lakes Interstellar Innovators, and Texas State Pastor Bobcat. Second place, best peer review, Tarleton Rellis LTV. And first place, best peer review, UH Clear Lakes. Okay, now for your efforts today, all those long hours put into your oral presentations. 4th place. In 3rd place, UT Arlington, 9. In 2nd place, Texas A&M. And top oral presentation, Texas State. So, combining all those scores, that was the magic Nina and I did during the last hour, computing the scores, calculating, trying to make sure all the numbers were correct. So, drum roll please for fourth place, top design team. Texas State, Light Camera Bobcats. Third place, A&M Aggies. Second place, Texas State Red Cat Central. And our top design team for fall 2025, Carlton Rose Engineering. All right, so if your team was named in any of those categories, stick around after this award presentation. Nina would like to get your picture up here for our records and to send to you. Some reminders. Congratulations, everyone. Another round of applause. This was truly an outstanding semester and one I will not forget. You're not done yet, right? Final reports are due December 5th. For your team funding, check with Talia. Check with TSGC on your institution status, on your team funding. Top teams, look for an email with instructions from Talia on getting your scholarships. And then also watch your emails for your team scores, all the photos we've taken, team certificates for those top levels, a showcase feedback form to help us make the spring even better. We have an independent evaluator that will be sending a survey from them to the students. Look for that form. And then in early January, we'll have our spring program announcement. So mark your calendars, April 13th and 14th, next spring is the showcase. We'll hope to see you then, and drive safely.